So, good morning to all speakers, faculties, and all participants of the second day of our FDP webinar. For today, we have three sessions. The first talk is by Professor Shikha Verma Madam from Institute of Physics, Bhubaneswar, and that is on the topic quantum effects and optical studies of nanostructures. The second talk will be by Professor Anjan Giri from IIT Hyderabad, and he will be talking about the dark side of the universe. And the third talk, that is in the third session after lunch break, that is by Professor Devakant Samal sir from Institute of Physics, Bhubaneswar, on topic emergent electronic phenomena induced by spin orbit coupling in the solids. And also, I want to request all participants to please interact with the speakers to make it more interactive session, and put your questions in the chat box. Now, I request Dr. Satpathy Samarpita Madam to give a brief introduction about Sika Madam before the start of the webinar.
Good morning, everyone. I'm Dr. Satpathy Samarpita, faculty of Department of Physics, OUTR Bhubaneswar, going to introduce the first speaker of day 2, which will be delivered by Professor Shikha Verma from IOP Bhubaneswar. We heartily welcome you, ma'am, to the FDP webinar. Professor Shikha Verma is currently working in IOP Bhubaneswar. She is an experimental condensed matter physicist working in the areas of surface, nanoscience, nanobio interactions, and ion beam application-based studies. Her field of research involves fabrication and modulation of quantum dots and nanostructures on a variety of surfaces like semiconductors, oxides, graphene, biomimetic platforms for understanding their optical response, transport behavior, and biosensing, and utilizing them for technologically important applications. Professor Verma completed her MSc in Physics from IIT Kanpur in 1984, and she received her PhD from the Syracuse University, US in 1990. She has published over 180 research articles in these areas. She was postdoc fellow at Case Western Reserve University at Cleveland, US, and University of Wisconsin, US. Professor Verma was also a visiting fellow at University of California at Santa Barbara. She is currently a member of SERV, PAC, CRG, SRG, NPDF, Power, WEA, and DST Kiran committees. She is the chairperson of Accelerator User Committee, IUAC, New Delhi. She is the editorial board member of Pramana and Frontier. With a short biography, I now request Professor Verma Madam to deliver the talk entitled as Quantum Effects and Optical Studies of Nanostructures. Ma'am, please.
Yeah, thank you, Satpathy. And on the onset, I'd like to thank all the organizers and especially Babita Madam for inviting me to this FDB program. It's always a pleasure to talk in CET now, which is called OUTR. And I'm very happy to be part of this. So I'll share my slides. Just give it me a second. You are able to see the slides?
Yes, sir.
Okay. Thank you. So I will talk about some quantum effects and some optical studies. Actually, I'll also talk about basically some quantum dot measurements and nanostructural measurements where we see these quantum effects. So lower dimensional materials display very interesting properties, and they are fundamentally different from the 3D materials. And so we have access to many of these dimensionalities, like zero-dimensional quantum dots and atoms, and if they are one-dimensional, they can be nanowires and carbon tubes. I'll show these examples as we go along. And 2D means they can be films or sheets or simple 2D surface. These will be called the film and sheets. So outline of the talk is something like this. First is an introduction to these different dimensions like 2D, 3D, 2D and 1D and 0D quantum dots. And then how we prepare these things, for example, lower dimensionality surfaces, and then characterizing. So you have smaller dimensions, like you may have nanostructures, quantum structures, or atomic structures. How do you even see these structures? Because, of course, optical microscope cannot show this. So you have to go to different microscopies and spectroscopies to see these kind of materials. And then I'll talk a little bit about graphene quantum dots. Graphene is a very interesting material, and that shows some quantum dots as well as interesting optical behavior, and then finally some applications. So to start with these lower dimensional materials, we all know these bulk material, but the very top layer is the interesting 2D material, and that is what, when we do our field of studies is started with surface science. So but then we are looking at the one atomic monolayer surface. This is what we are calling as a 2D. And if we look at the atomistic picture, it will look something like this, that on the top is this single monolayer, single atomic layer, which is called the 2D layer. And then, of course, you have a whole bulk sitting under it. So these, whether it is surface or you have 2D material, or surface is anyway a 2D material. So surfaces or other 2D materials like thin films or sheets, or 1D material or 0D material, which is called the quantum dot, depending on what kind of structure you have, this will control the properties of the material, whichever material you are studying. And the atomic arrangements will change the surface properties. And this is true for 2D as well as 1D structures, and also in quantum dots. And one can deposit these quantum structures and nanostructures. And how we create and deposit is, I will show in the previous slides. And then one also studies the interaction of surfaces with atoms, molecules, biomolecules, and among themselves also. And these are the properties that get changed. When the material changes from 3D to 2D to 1D to 0D, all these properties will show changes. So for example, absorption properties. Now this absorption can be optical, in the optical regime, or in UV regime, whatever. Their absorption properties will change, sensing properties will change, conducting properties. So optical properties I'll show a little bit, tunneling effects I will show, that what is the tunneling effect and how are we able to see tunneling effects from these quantum structures or nanostructures. Catalytic properties also change, and electronic and optoelectronic properties also change. So the same material, whether it is in which state, 2D, 1D, 0D, or 3D, will show various interesting properties. And that's what we want. Our goal in our field is to tap these properties and use them for benefit our applications. So for example, we all know what the gold looks like. But as soon as, so these are some of the optical properties. So we are looking between 3 and 30 nanometer, it will have this color. So it depends on the size of the particle as well as the material properties of the particle, whatever material you are studying. And gold clusters, which are less than 1 nanometer, become quantum regime. Even in 3 nanometer, it will have some quantum regime. And then the atoms, of course, are colorless. So this is the range, and that's why you see a variety of interesting colors here. So the interesting thing is that this is not new. The first nanotechnology, these are known in churches in Europe, that these stained glasses are there. And for a long time, it was not known how the stained glasses were prepared. But now we know, in the recent time when the studies have been done, what we have seen, that the gold particles of various size shows these colors. For example, if there is a circular nanoparticle or a spherical nanoparticle of 25 nanometer, it will show something like this color, red color. And 50 nanometer will show this color, and 100 nanometer will show color. The size and shape is also important for this kind of shapes. And on the other hand, the silver particles show this kind of color. So these stained glasses actually contain nanoparticles of gold and silver. How they were done is not, they, of course, in these times, in this 600, 1700, they did not know how to prepare nanostructures. But what they are doing, they are working with the colloid solutions. And when they are making these things, they are just doing this grinding. And what they achieved was these colors. So they knew they were following some recipe without knowing that what exactly they are doing. But they knew that this kind of recipe will get this kind of colors. So in ancient stained glasses maker knew that by putting varying amounts of gold and silver in the glass, they could produce the red and yellow found in the glass. So this is something very interesting and which catches your eye. Okay, the nanoparticles can produce such beautiful colors. Okay, so this is another example of nanoparticle, and this is like 4th century AD. So this has even interesting properties. These are, of course, again, it has gold nanoparticles inside. But now this one, the figure on the left, you are seeing when the light is falling on it from front. Whereas the B, or the one on the right, is the cup, same cup, it is called, it's a very famous cup, Lasargas cup. And in this case, the light is falling from the behind. So this is in reflection mode and this is in transmission mode. And the colors are different, and this is again happening due to the presence of gold nanoparticle. So when illuminated from within or in transmission mode, the Lasargas cup glows red. The red color is due to tiny gold particles embedded in the glass, which have absorption peak around 520 nanometer. So why these colors are coming, as we go along, I'll go to this. So these cups are there in the British Museum, London, and you can see this. So why these colors are coming up? So you all may have studied in your solid state that the density of a state. So for example, for a 3D material, the density of a state looks like this, goes as root to the E. This is x-axis is the energy, and this is the density of a state. Whereas for the quantum, well, it looks something like this, and this is for quantum wire, one dimensional, this is 2D object, this is 1D object. Whereas for the quantum dot, if you see, these are very well-defined energy states which exist. And so as we go along, we will see this. So some applications of quantum dots are in, of course, we saw in optical properties, solar cell, photocatalysis, lasers, LEDs, and of course, biology also. So this is another example. This is the tunable properties of cadmium selenide quantum dots. Again, it's a similar property. So here what is being done is one is looking at the fluorescence as a function of wavelength. Okay. So, or one can also look at absorption as this is the fluorescence. And one is seeing that when the size is big, the color of fluorescence, the color that is being given during these fluorescence measurements is in somewhere between around 650. And this is what is imparting a red color. We know these wavelengths, these are all in optical regime. So because this fluorescence is in 650 wavelength, so hence the color is red, and so on. So very small particles have a color in blue ring. And why this color is coming, I'll just go to the next slide and then we'll show. But the interesting part is, this is as the size of the particles is changing, as the size of these nanostructure is changing, or as they are becoming quantum dot, they are showing different colors. So size tunable fluorescence spectra of CDSE quantum dot, and the sizes, for example, are varying from smallest is something like 2 nanometer, this particle, and going up to something like 8 nanometer. So this is what is imparting the color. So if you look at this energy diagram for a 3D material. So this is a 3D material, and you have a valence band and you have a conduction band. And when electron, some photon may strike, or you may create an electron hole pair. So when you excite an electron from the valence label to the conduction band, you create an extra electron in the conduction band and you create a hole in the valence band, and these together make a exciton. This exciton is a very important element. So suppose you have a bulk and you have an exciton radius. This dashed line is the exciton radius. So that gives the physical picture of in which radius the exciton is stable. So suppose your exciton radius is this AB. Exciton radius is AB, and your bulk, your material is bigger. If your material is bigger than your excitonic radius, you will have different effects, okay? But as you will reduce the size of your material, once your material becomes smaller than the excitonic radius, then the band gap increases, the size of band gap increases, and you will start seeing some discrete energy levels. Here, it is all a band. Everything is a band, and you will have some kind of a band gap you will see. When your material becomes smaller than the excitonic radius, now your excitonic radius is somewhere here. This thing is telling you the excitonic radius, and your material has become a little smaller than the excitonic radius. Then you will start seeing the increase in a band gap as well as some discrete energy levels. Okay, when your dot becomes, when your size of the material becomes even smaller, the band gap increases further and the states become more discrete. You will start seeing these discrete states. And same thing continues to happen. Now your particle is very small, suppose quantum dot, or much smaller than excitonic radius. You have very discrete. Now your band gap has increased. So when band gap has increased, the energy of fluorescence will increase. And because the energy of fluorescence increases, the wavelength decreases. This is what is showing here. So you see that the wavelength, here you are not even, whatever is the band gap, you will see something like this for the 3D material. Your absorption versus energy, what energy it is absorbing is, say something, it is a semiconductor. So this portion will tell you the band gap. But as you make your dots smaller and smaller, two things are important. One thing is their color. Color is becoming larger in energy or smaller wavelength. This wavelength is the smallest. Red is the longest wavelength, whereas blue is the smallest wavelength. Or this is the maximum energy. Highest energy, say, is because this band gap is largest for the smallest particle. And this band gap is the smallest. So this gives the red color. And the states are discrete. Because the states are discrete, you are seeing a special profile. If the states are not discrete, you will get some kind of a continuum. But these discrete states will tell you a specific profile. Discrete functions at the when this fluorescence is taking place. So the absorption or fluorescence, this is the absorption. So that's why this color starts to become, this is what gives you the color. Size, as the size becomes smaller, the fluorescence that will come out is of larger energy. So that is one thing, but this is not the only factor. The material properties will also play. For example, which wavelength you are absorbing more. Sometimes material characteristics also play role, but this is the main reason why your colors change. That you all see variety of colors is as your band gap is changing, the energy that is you are absorbing or you are releasing will depend on the band gap and this discrete states. So this leads to the quantum confinement, leading to the size-dependent optical and electrical properties that are distinct from those of parental bulk solid. Occurs when the spatial extent of electronic wave function is smaller than the Bohr exciton diameter. Here AB is the Bohr exciton diameter, whereas D is the size of the particle, diameter of the particle. And so you see variety of band gaps. For example, in the case of indium antimonide, depending on the size, the x-axis is the diameter of the particle. Depending on the size, you see variety of band gaps. And you know, if you will see variety of band gaps, that means you will see variety of colors. So that's what these variety of colors can be seen for indium antimonide. Similarly, variety of colors can be seen for all these 3, 5, and so on. This is zinc oxide, this is anatase, and rutyl is for TiO2, and these are the very, very small diameters, right? So somewhere we are talking about diameters between, of course, these are very small, but about 40, 50. So size of the dots we are talking about is about less than 40, maybe mostly in the range of 1 to 10 nanometer. So in quantum confined semiconductor nanostructures, there are some special things which are going on. Electrons exhibit distinctive behavior compared to that of the bulk. That we have seen that the band gap increases and discretization of states takes place. This enables the design of materials with tunable chemical, physical, electrical, and optical properties. And this offers a strong light absorption and bright narrow band emission across the visible, and it can also be in infrared wavelengths. These properties are of interest for imaging, solar energy harvesting, displays, and communications. Prospects in technologies such as displays and lighting, laser sensing, electronics, solar energy conversion, photocatalysis, and quantum information. So the area is vast where these quantum dots can be used. Nanostructures also, quantum dots also. So how do we prepare such structures? So I talk a little bit about that. So there are mostly two approaches for these things. One is a top-down approach, where you remove the material to make nanoscale objects or quantum structures. And the other one is bottom-up approach, where you assemble nanoscale objects out of even smaller units, for example, atoms and molecules. So to tune, and the goal is, of course, to tune the properties that we want by designing desired structure. So this is the first. Let me talk a little bit about equilibrium growth, and then we'll go to the non-equilibrium growth model. So in equilibrium growth model, what happens? So you have a substrate, and you start putting some material on the substrate, and you will have a growth which is layer by layer. So this is the first atomic layer, and on top of that, the second atomic layer grows, and this is called layer by layer growth, or it's also called Franger-Murphy growth. In the other case, what happens is that the islands form. There is no, if you see, there is no complete layer on the surface. This is the substrate, the top layer we call as surface, and then we are putting atoms on the top. So here only island kind of structures are forming, and this kind of growth is called Volmer-Weber growth or islet growth. And then in the third case, you have a layer, first layer, as well as then you have islands. So this is layer by layer growth as well as island, and this is called the Stransky-Krasnov. This is a very important growth also for the development of quantum dots and nanostructures, which give beautiful lasing properties. So this is what the another top view shows, that here it is all layer by layer, whereas here you are putting the atoms on the top, which are growing in island type, and here it is layer by layer along with islands. Then we go to the molecular beam epitaxy. Here what you have, here what you are putting atoms are at a very slow rate. The rate is slower than the diffusion of the atoms on the surface, so you have non-equilibrium growths taking place. Molecular beam epitaxy is a versatile technique for growing thin epitaxial structures made of semiconductors, metals, or insulators in ultra-high vacuum. All this happens in ultra-high vacuum. A beam of atoms, or more general beam of molecules, is directed towards the crystalline substrate such that the atoms or molecules stick at substrate surface, forming a new layer of the deposited material. This is the one molecular beam epitaxy system, which is also present in Institute of Physics. And this is the called the Knudsen cells, where the material is present, which is evaporated and deposited on the sample, which is sitting. This is the sample transfer arm. Sample is sitting somewhere here, and it is evaporated and deposited. Everything is under ultra-high vacuum. So again, these are the Knudsen cells that can have variety of materials. For example, here it is shown arsenic, gallium, indium, argon, phosphorus, and they are deposited, and that's how the this film can grow. So these materials bombard the surface, and these layers can be grown. Another process by which we can create structures, nanostructures, or smaller nanostructures leading to quantum structures is by ions, bombarding of ions, and this is a top-down approach because the bulk is already there and it is chiseling away the material. So this is our ion implantation facility. We have a 3 MV accelerator and we have a low energy negative ion facility. So this Pelletron accelerator is 3 MV and the low energy is 330 kV negative ion facility. So in case somebody is interested in doing ion implantation, this low energy facility is already operational. On the 3 MV accelerator, we may start giving beam time in next 1 or 2 months. And these are the various other lines for RBS Pixie implantation in our beam hall. So the various effects that take place during this ion implantation. So we are putting the ions, using this facility, we can put the ions in any material. And when you put the ions, you are also making structures on the surface, as I'll show in the thing. And this structures on the surface happen due to the inelastic effect. So the surface modification is going to take place. The ions, when you are bombarded on the surface, this is the incident ion and this is the surface. When the incident ion is bombarded on a surface, the ions go inside. They will create some defects and collisions in the material and they will get bombarded. But during the process, when the ions bombard on the surface modification also takes place. And that's what, at least in this talk, that's what we are interested in. But there's a lot of work going on in this region of the material, which is an important because it changes the material properties. So after surface modification, this is what the surfaces look like. For example, this is TiO2, for example, sample, just maybe any 110 rutile anatase, depending on what you want. But in these figures, it is a TiO2 110 rutile surface material has been taken and bombarded with 60 kV argon ions. This is the clean sample what looks like, but as you keep bombarding, you see first small nanos. This is by the way AFM images, atomic force microscopy images. Something about these things I will tell you as I go along. So these have a height information, what the surface looks like. The size of this image is 1 by 1 micrometer square. Okay? So this yellow color shows that it is height. Okay, and the more yellow, that means higher, and the redder means it's bottom. So you can clearly see that at this stage there are nanostructures yellow color, which is very, very small, but this become bigger. This is the fluence. What is written here? Fluence means we are bombarding these 60 kV argon ions at this fluence. That means these many ions per centimeter square have been put into this material. So the dose is increasing. And as this dose or fluence increases, you see that a variety of patterns are forming on the material. And initially, they are small nanostructures, or as we will show, these are very, very small, maybe even the quantum regime. But as you put more fluence, they take variety of character. And these are actually becoming ripple-like or almost one-dimensional. And so as the fluence increases, we see that the dot size or this nanostructure size is very small. In the beginning, it is only 5 nanometer, and then it is changing as the fluence is changing. So again, how do we how do we study these kind of nanostructures? How do we understand what is their size? There's a very important technique. These are the two important techniques. I'll probably just discuss the first one. I may not have time for the second one, but the two techniques are similar. In a scanning tunneling microscope, we are measuring the tunneling current, whereas in the atomic force microscopy, we are measuring the forces. And the tunneling current we are measuring between the surface and the tip. I will just show you. So using this, whether it is STM or atomic force, what does it do? So you can even see atoms. You can study the surfaces and various interesting properties of the surface. You can study the interaction on the surface. For example, you can do physics, chemistry, biology between the atoms. You can put atoms on the surface and monitor changes. So the development of scanning probe microscopy, these two people, Benign and Nora, got Nobel Prize for the development of STM. And they had seen, since you can see atomic resolution, they got Nobel Prize for seeing a 7x7 structure of silicon. This I will show you. So this is what is the mechanism of scanning tunneling microscopy. And since it involves tunneling, so that's why this technique I have kept, in the sense that this is a talk on quantum effects, and tunneling is a very quantum mechanical phenomena, as you may know. So there is a tip and there is a surface. Okay, this is what surface we want to see, what it is like, if they have quantum structures or nanostructures or 2D structures or atomic resolution, whatever we are interested in. You apply a small bias. So for example, this is a very small nanovolt bias between the sample and the tip. So sample is suppose negatively biased, your tip is positively biased. There is a very small separation between the tip and the surface of the order of 5 to 15 angstrom. Okay, so it uses the principle of tunneling, has a sharp metal tip very close to the conducting surface, and the bias voltage between the sample and the tip is applied, and the separation is 5 to 15 angstrom. Since the tip is not touching it, but there is a small bias, electrons tunnel from, even though there is a space, they tunnel from the surface to the tip. And this rate of tunneling is very sensitive to the separation D between the tip and the surface. Okay, so as we go along, so this is the energy level diagram of the sample. It is not very complicated, just let me explain in a few minutes. So this is the energy level diagram of the sample, and this is the energy level diagram of the tip. So suppose this is the Fermi level, bottom below Fermi level states are filled, and above Fermi level states are unfilled at room temperature. And similarly for the tip, this sample is conducting, tip is also conducting, it has a Fermi level. Again, these states are filled and these are unfilled states. As you apply a bias, I say you apply a small bias, this delta V. As you apply a small bias, your to the substrate negatively charged, your tip is positively charged, your Fermi energy rises a little bit. So what happens, this Fermi energy is slightly higher than that. So electrons from the filled states of the sample will tunnel. This is a D. There is a separation between the sample and the tip. These electrons will tunnel from the filled states of the sample to the unfilled states of the tip. And this is what is the tunneling current. The tip and the sample are not touching. They are slightly away, but this separation is very, very close, few angstrom close. So the electrons can tunnel from here to here, and this gives you the tunneling current. And the special thing about this tunneling current is, so this is the wave function of your tunneling probability. This is the probability, this is the wave function. And this gives the tunneling current. This I is exponential to -2 kappa d. This is your kappa, but phi is the work function, which is of the order of 1 nanometer inverse. But the thing is, this is the important fact, that this depends exponentially on the -d. So as your d decreases, as your separation between the tip and surface decreases, the current increases exponentially. So this is what, as the tip comes closer to the, see, tip is going like this. Tip will just move from here to here. When this separation is small, current will be huge. When this separation will be large, current will be small. And this gives you the profile of the surface. You exactly know what your surface is looking like. So this tunneling current varies exponentially with D, and STM probes the, basically it's probing this electrons which are going from here to here. And these are some early STM images. Let me show you good ones. So this is a surface and this is the tip. It probes, and then you have you can apply a negative voltage to the surface. Then you'll probe the electrons going from the surface to the tip. You can have positive bias, and then you'll have electrons tunneling from the tip to the surface. You can do all these things. And this is what a silicon one surface looks like. This triangular thing. And if you look from top, this is what it looks like from the side view. This is, so this orange atoms are the top atoms. And this is the 7x7 reconstruction of the surface. When you cut a bulk, the top surface will not remain what the bulk is, it will show some kind of a changes on the surface. This is the now what we see a 7x7 structure is something like this. It's a beautiful structure, and this unit cell is something like 4.6 nanometer to 2.6 nanometer. These are again same silicon one by one. One, when you are probing, the tunneling is happening from the surface to the tip, and here the tunneling is happening from the tip to the surface. These are various. So now what you are looking is at atomic resolution. For example, if you look this portion of the silver surface, you are looking at the silver atoms. Here also it is all atomic resolution. What you are seeing is the atoms on the surface of the silicon. So STM is a very powerful technique in that, and this is also, it's giving some hexagonal silver island, and the size is something like 9 nanometer of this. It's one molar layer, one atomic layer. So these are various things which I'll not go into. So you can make this kind of structures also. This is something like, so iron atoms, this is like 48 iron atoms sitting on copper 111 at 4 Kelvin. And this same STM tip can be used. First you drag the, put the tip on the thing, then you change the current, and you can make these kind of coral structures. These are quantum structures. Diameter is something like 14 nanometer, 14.25. And these things you've seen inside these waves are the standing waves actually, this. So these concentric rings that you are seeing are the variation in the local density of a state, that what we talk on a 2D surface. And these electrons are tagged inside this coral thing. This is also some xenon atoms which have been placed on nickel 110 surface. This again, everything done using STM. These are some quantum structures of MOS2 on cold surface, grown by MBE and investigated by STM. So nanoparticles can catalyze chemical reactions, and important thing is they can be used for reducing pollution via these oxidation reactions. So let me just, the remaining time that I have, I'll just say something about the graphene quantum dots, which have been prepared in a monolayer graphene after ion addition, and some of their optical properties. So graphene, as you may know, is considered almost a wonder material. It's a 2D material. So, and the Nobel Prize for graphene was given in 2010 to Gaim and Novoslav. So, and graphene is nothing but when we write our pencil, it is we call it lead, but actually it is graphite when we write. And if you get a very, very small, if you can make it a single layer, then basically it is graphene. And the way the first graphene was prepared is you put it on sellotape, and then you keep peeling off the layers. When you get left with a single layer, that is what is a 2D layer of graphite, or it is called graphene. So this is what the graphene looks like. It is a single layer of carbon foils. It's all sp2 bonded. And the carbon atoms are densely packed. This is like a benzene type rings. And it has some very special properties. For example, 1 square meter sheet weighs only 0.77 milligrams. And the CC bond length is given here. And graphene sheets stacked to form graphite with interplanar spacing of 0.335. So it can show all these structures. For example, this is a 2D layer of graphene. If you put these 2D layers on top of each other, there's a van der Waals interaction between them. This is the 3D graphite that we were talking about. You can fold them, and then they can make tubes, one-dimensional tubes, and you can also make fullerene, spherical structures out of it. This is an STM image of graphene, what it looks like. This is the 2 layers of graphene on each other. So graphene has exceptional strength, thermal conductivity, and electrical conductivity. So it has some very interesting properties. And with more than 10 times better electronic conduction properties than silicon, graphene is considered silicon's ideal replacement. This promises to deliver electronic devices much faster, more flexible, and more efficient than their silicon analogs. However, roadblocks for making such devices with graphene is the lack of sizable band gap. It has no band gap. Actual graphene, as I'll show you, does not have a band gap. So we have to open the band gap to do any important work in its electronic energy structure. So this is the band structure of graphene. It is not complicated. So this is the k-axis, momentum space, and this is the energy. And if you look at just this point, this is at the k point, there is no band gap here. The two are just joining. In band gap, we mean there should be some separation so that electron can go to the conduction band and exciton can be created. So the valence and conduction band, that is pi star band, show a linear relationship between electron energy and moment. And this makes graphene a zero gap material, which conducts electron like a metal. So this has it has a very high conductivity because it behaves like a metal. Aim is to understand and manipulate this 2D material and make it better suitable to use in the electronic devices. So this is a very important aim in present day studies, that to open this band and manipulate graphene for doing some applications, because it has such wonderful properties. So graphene on the nanometer scale opens up a band gap, providing interesting optical properties. So if you can open the band gap, it can show interesting optical properties, which are some of the properties I'll show. And nanoscale graphene is important due to promise related to photovoltaic devices, nanosecond lifetime, bioimaging, catalysis, molecular scale electronic devices, light emitting devices, and phototransistors. Some graphene QD prepared by hydrothermal method, organic synthesis, and electrochemical techniques. So graphene quantum dots have been prepared by these rules. What we are doing here, what I'll show in this study, is some quantum dots that have been prepared using ion beam technique in our institute. There are several limitations since these graphene quantum dots do not show any visible light absorption or prominent UV response unless they are doped, functionalized, or integrated with metal particles. So what we have done, we have taken a single monolayer of graphene and bombarded it with argon ions. And energy used was something between 100 and 300 eV, and the fluence, ions per centimeter, is 10 to the power 14 ions per centimeter square. And then after that, this is a single layer graphene. It is also called monolayer graphene or single layer graphene. And we have done Raman of this. And so what ion implantation does is introduces point defects in graphene, and which will scatter phonon, influencing the frequencies. So let me just go into the Raman. So this is what Raman is telling. And what is Raman technique? Is when you have some material and you shine light, there will be a reflection at the same frequency, but there will also be shifts in that laser light. And the shifts is what this Raman spectrum is. And the shifts tell you how much frequency, how much shift in frequency of the inelastic scattering. So this is inelastic scattering, which the Raman light shows. And this has some beautiful signatures for graphene, in the sense, this is the clean graphene, what it looks like. This is the important feature, G feature. The clean graphene will show one G mode and 2D mode. This will tell you it is a very good graphene, single layer graphene. But as you put in defects, for example, we are putting ions in the material, so we are creating defects in the material. You see this one peak, which is a D peak. This is related to the defects. So initially the defects increase, but this D mode is due to the breathing. This modes which are breathing, this is, so once the defect is so much that some of the atoms have gone away, the breathing mode of graphene will reduce, and then the mode starts to reduce. So what we have studied by absorption method or optical absorption method is what happens to these materials once they have got some defect in them. So this is what the AFM picture looks like. So AFM is very similar to STM. Only thing is here we are measuring the forces, the van der Waals forces between the tip. Again, we have a tip and we have a surface, and we are measuring the forces, van der Waals forces between the tip and the surface. So this is to 200, the two techniques otherwise are very similar. So this 200 by 200 nanometer square surface is there. And then as we put argon ions of 100 eV, what we see, we are seeing some bright spots. And these bright spots are nothing but the defect that have been created in the material. But along with defect, you will see there are some black spots. And these black spots are the graphene where defects have not been created. And as we increase more and more energy, we see the size of these bright spots increase and the dark spots decrease. Dark spots means that the graphene and the graphene size is becoming smaller. So these are becoming basically graphene quantum dots at this 200 eV. Here also, this is the same thing. The defect increases and the graphene quantum dot size decreases. So we have measured how much is the size, quantum dot size from these AFM images. See, these are 200 nanometer by 200 nanometer square. So you can, these techniques, both STM and AFM, you can measure what is the size of the defect as well as size here. That is the biggest strength of these techniques, that you get these numbers with the accuracy of atomic resolution. And one can find the size of these quantum dots. This is the size at the energy that we have implanted, and what it looks like that at the energy of around 100 eV, the quantum dot size is less than 10 nanometer. And in this range, they are between 10 and 9 and 10 nanometer. And this result we are getting from our AFM studies also, as well as from the Raman studies. This is some XPS, let me know. And this is the photo response of the nanostructures. So this is what, if you, let's first look at this black curve, and this is the clean graphene. So if you will see, notice that it has a feature here, some peak here, there's mild peak here, but then it is more or less flat. This is the very important part of the graphene, that it has no structure. This is the optical range. If you'll see, these are the wavelength and this is the absorption. What we are studying is the absorption measurements as a function of wavelength. So graphene does not absorb anything, as we have seen that it has no band gap. Since it has no band gap, it behaves like a metal, and absence of band gap, it will not absorb anything in this range. But what you see that as we put more and more, for example, even at 100 eV argon ions, when we have put in the material, this UV range, this is the UV part up to here, where is the UV part. The UV part increases, absorption in UV range increases, but as well as you will see that there are some structure here, absorption here, and this is already telling us that some band gap has opened. Okay, the band gap opening is the most important part, but then we see that the best profile, good profile is here also, right? 250 EV pay. We are seeing that this photo absorption is very important, that shows that the band gap has opened, and we can use this absorption. This is exactly like the absorption. That means it is giving this color, whatever this 550 color is, something like reddish green color. It will give this color. Okay. So just like I showed the colors for the gold nanoparticles or for the CDSE nanoparticles, this graphene will also be showing colors depending on what size of graphene quantum dots are present. And we know the size of the quantum dot from here. So this is the beautiful colors we are getting from here. And the various peaks designation is, in the case of pristine, this is the pristine, clean graphene. This peak here is due to the pi star transition in sp2. And then this near wavelength independent, and then, but after that, it is between 500 and 800, there is no absorption. But after irradiation, there is an appearance of mode at near 540, and this is related to the formation of graphene quantum dot in the material. And there is a 70% enhanced UV photo response after 150 EV irradiation. Argon ion irradiation at 150 EV, what we are seeing is the presence of these things. And this is in absence of any nanoparticle in the material. There is no metal. Most of the earlier studies have seen this kind of band opening with metal, but here we are doing it without any metal. But we are putting in defects, okay, controlled amount of defects, so that we are able to So we contain the region where the crystalline graphene is present, and that gives us the presence of graphene quantum dot. So quantum confined nanostructures achieved by ion irradiation present rich and interesting absorption behavior. So these are various applications. For example, these colors I have told, the size dependent absorption methods, but then these are numerous things. And one very important application is in bioimaging. In bioimaging, what they do is, for example, in the case of cancerous cell, they know what are the antibodies. They have quantum dots, and on the quantum dots, they functionalize them with antibodies for the cancer, and then they put in the bloodstream. So the antibody will go and attach to the cancer cell, but when it will attach to the cancer cell, it will also have a quantum dot attached to it, and these quantum dots will have absorption optical properties. So when you will use even UV laser, they will fluoresce, and this fluorescence will tell how much one can quantify the amount of cancer in a body. So this is has massive applications in the case of bioimaging and medicine, but then also it has energy harvesting in photocatalysis. When you use nanostructures, you can have a better photo harvesting because of their band gap changes. So in summary, of course, this summary is about graphene, but what I have tried to give some idea about how the optical properties change as the band gap changes from 3D material to smaller sized material. The main idea is that the band gap increases as the size becomes smaller and smaller. And then how you see these kind of quantum structures. Of course, I talked about one of the technique is quantum tunneling for measuring these very, very small structures. Atomic force microscopy is another one for which I did not have much time, but the two techniques are very similar. The atomic force microscopy is very important in the sense that you don't need a conducting surface. For scanning tunneling microscope, you need a conducting surface because you have currents to measure. So your surface is conducting, your tip is conducting. In the case of atomic force microscopy, you can have, for example, we are studying TiO2 or which is not which is semiconductor, not a metallic. So for these kind of surfaces, even for biological surfaces, it is atomic force microscopy that can be used, and both give kind of a atomic resolution. So you can look at the surfaces. We are forming the structures using two techniques I talk about, MBE and ion implantation. But you have tons of techniques. MOCVD is another very important technique for making these 3-5 kind of nanostructures: indium phosphide, indium arsenide, indium gallium arsenide. This is enormous work is there, and where they use it for lasing properties. They put quantum dots in indium gallium arsenide on gallium arsenide, and those hot kind of clusters, quantum dots are formed for laser applications. So which is also another one. And what I have showed you mostly for the graphene quantum dots, that they are prepared by the ion implantation, and we can see the optical properties that the band gap is opening around 560 nanometer, and we are able to see UV and increase in UV as well as visible response. So okay, thank you.
Thank you, ma'am, for your insightful talk. It was really interesting and informative. We have a few questions from the participants.
Yeah.
The first question is, how can we get... okay, the first question is, can you elaborate how the colors change with the size of the nanoparticles?
Yeah, just give me a second. Yeah, so this is the main thing. See, so if you have the 3D material, you don't have any discrete states. We have bands in the valence band as well as conduction band, and there are no discrete states. We have some band gap. So this absorption absorption is what light it is absorbing, will be something like this. If you, this is the light that you are absorbing. But as your size becomes smaller, your band gap is increasing. But in addition to your band gap increasing, okay, your states are becoming also discrete. Because the states are becoming discrete, so your this profile of absorption, you will have some kind of enhancements, increases, and these will also become, they will come as a peak rather than a continuum. And this color of fluorescence, if it is, we are talking in the terms of emission, if we are talking of the emission line, this emission electron, so for example, electrons get excited here, electron will be here, hole will be here. When the emission takes place, this electron will come down to occupy this vacant place and some light will get emitted. The emitted light will depend on this band gap, right? Again, so emitted light is what we are seeing. So if the band gap is small, the emission energy will be small, whereas if band gap is large, emission energy will be large. So large energy means towards the blue color, whereas the small energy means towards the red color. So depending on this band gap and depending on the material, you will see a range of colors. So that is the idea. So for example, in this figure, what is shown, that when the band gap is smaller, the emission will be of lower energy, and that may be red color. And when the band gap is large, the emission will be of larger energy, which may be of blue color. And since the discrete states are there, the color will be very discrete. You will see discrete colors.
Okay, ma'am. The next question is, how can you define the exciton radius? How can it be correlated with the particle size?
Yeah. So exciton radius is this. So you have an electron and hole pair created. This electron and hole pair is bound pair, and in how much distance is this exciton is present in physical space, how much space this exciton is present, because this exciton may have face recombination and may disappear. So if it is in the bulk material, you will have some excitonic radius, okay, and this electron hole pair is what is giving us the absorption as well as the emission. So this is the important factor which is required. So one thing is this electron hole pair has to get created, and on the other hand, this electron hole pair has to remain stable in the system. So if it is in the bulk, it may do the recombination electron which is going here, will become disstable. It has to remain stable and it has to remain within the volume. So this is the factor of exciton radius. It is basically, exciton is basically the electron hole pair which is bound, and that is being compared to the size of the quantum.
The next question is how the mode of transmission and reflection are affecting the colors.
Yeah. So see, the thing is, suppose we talk just about the emission. So emission, we are seeing that the emission we are talking here, or the absorption we are talking here. Absorption is the light that the material absorbs, and emission is the light that it emits when this electron hole pair rejoin, exciton is lost. So the two, everything depends on band gap, but there may be some other material properties may be happening. For example, gold, we see that the gold absorbs some color. Okay, so the thing is, so absorption is one thing, and absorption and emission are not the only factors. There is also scattering, and we know scattering goes as 1 to the lambda 4. So, for example, the smaller wavelengths are scattered more. So all these factors together will decide what color we are seeing. So absorption means what light is getting absorbed when electron hole pair is generated. Emission is when the electron hole pair combine, then what light is given out, and that is can be in photoluminescence form or it can be in fluorescence form. So all these together will decide the color. But as we have seen in the case of CDSE, this the color.
Okay, ma'am. The next question is, what does it mean by negative ion beam?
Okay, so the thing is, okay. So the thing is, when we produce the ions in this beam, the initial particles which come out of the source are negative in nature, and their negative ion is not stripped off. So when you implant in the end, it's a negative ion. On the other hand, in this our pelletron, what happens? Again, the particle that is generated somewhere here will be negative, but when it comes to the pelletron here, in the center of the pelletron, we have a stripper gas. And the stripper gas is a nitrogen stripper gas, and the purpose of that gas is to remove the negative ion. So during that stripping process, negative ions are removed and the respective ions become positive in nature. So in the pelletron, when the ion is implanted, it is positive in nature, whereas in the case of our negative ion implanter, the ions implanted are of negative type.
The next question is, why the impurity peak decreases in size for the increase in impurity concentration in Raman scattering?
Uh, yeah, I didn't go into the detail of this. Yeah, just right. Okay. So this monolayer graphene, it has two modes. One is G mode and one is D mode. So G mode is actually the stretching mode. The Raman is basically vibrational spectroscopy. So it registers all the vibration, phonon modes or vibrational modes that are happening on the thing. So this kind of vibration is a stretching vibration character. And stretching will still continue. See, so this breathing will continue up to some time. So suppose this atom goes away, breathing of this section will stop or change. If this atom goes away, breathing of this section will go and stop or it will change. At some point it will happen that the total breathing will stop, right? So the breathing mode is the D mode, whereas stretching mode is the G mode. So as we are putting more and more ions in the material, you will see at some, that is the property of the material. This is graphene is like that. Graphene, as you know, has a very high conductivity. The conduction is like a metal, and so it has no band gap. That is the material. That's what I was when this question was there for transmission and absorption. The size are important, but the on top of this is the material property which is important. So clean graphene without any defect has no band gap in it. And the idea is actually to open this band gap for doing any electronics or any optical studies. This pi star, actually they are joining together. There is zero band gap. It is actually it's called as it is called, it's a zero band gap material, or it's called a Dirac material. That is because these are linear. Both the signs are linear and meeting at this point. It's called a zero band gap material. That is the material property.
The next question is, what effect will be expected if nano defects are created instead of ion implantation?
Yeah, so nano defects can be created, and one will have to find what ways to create.
Good afternoon, everyone. So the next talk of the day will be delivered by Professor Anjan Kumar Giri from IIT Hyderabad. We highly welcome you, sir, to the webinar. Professor Anjan Kumar Giri completed his PhD from Utkal University, Bhubaneswar, and is currently working as a professor in IIT Hyderabad. His research interests are flavor physics and CP violation, neutrino physics, and BSM. He has more than 280 research publications. Now, I welcome you, sir, to give a brief introduction on the visible sector of the universe and discuss some aspects of the dark side of the universe. Sir, please.
Yeah, thank you very much for the kind introduction. And I will share my slide. Can you see my slide?
Yes, sir. Sir, slide. We're not able to see the slide, sir.
Are you able
Yes,
to
sir.
see now?
Yes, sir.
Yes, yes, visible.
Okay. So let me start. Um, First, let me thank you, the organizers, for giving me this opportunity to speak on this faculty development program. What I'm going to tell is towards the dark side of the universe. Here, I'll try to connect first with the visible sector that we know, and then try to motivate that why we need to uh, look into this aspect. Okay. Is that okay now? Everything fine? Are you able to see, right? Hello?
So now it is visible.
Okay. Okay, I'll just start with this thing which appeared a few days back, that terrifying 160-foot monster asteroid moving towards Earth at a speed of, let's say 3 lakh kilometer per hour. This was warned by NASA. So, do this kind of news create some kind of a curiosity what actually happening? Once in a while, we read this kind of news that some asteroid is heading towards Earth. We might have also heard that if there will be some solar storm, then our network, which we are completely dependent through satellites like the internet network and many other things, will be kind of broken. So we'll be completely disconnected in this digital world. There are a lot of ramifications. So there are many things that we also need to know in addition to the other things that we are looking at. So my talk will be basically in that direction. There was the beginning talk, which is so there are roughly 4 talks that I saw that which will be more or less kind of related to my talk. The first one was the one which was the introduction talk given by Professor Ajit, and then last one of this meeting will be at the end and QGP. And there are 2 more talks related to neutrino physics also. So somehow will be some way related to those talks. So my plan of the talk is like this. I'll give a brief introduction and then try to say a little bit about standard model. Then I'll come to what is called the baryon asymmetry of the universe, why we see only the baryons, why not the antibaryons, or why we see matter and why not antimatter. And this will lead me to something at the end, something called invisible or dark sector. Of course, the invisible neutrino sectors will be covered by 2 speakers. And then I will try to skip those portion. I will look into only the dark sector, and at the end I will give a outlook. So these are some eternal questions of mankind. What principles govern energy, matter, space, and time at the most elementary level? What is the world made up of? And how does it work? Uh, if we know it or not. What is the mass? Actually, this is the idea started with Newton, and recently we found the Higgs boson at the LSC, which actually try to explain how the different kind of particles get mass. Of course, we all are massive particles basically as such, and we consist of these fundamental particles. And how do they get mass? It's kind of understood through the Higgs mechanism. But as we see during the talk, that there are many other things that we don't know. So that will also be kind of a question to be addressed. Where there is no antimatter in the universe, because all of us consist of matter, and we don't see any trace of antimatter to very large, like 10 kiloparsec distance. If there is a antimatter and if we consist of matter ourselves, all of us, you observe the table, chair, or anything that you can see or touch consist of matter. Otherwise, if you touch it, then matter, antimatter will annihilate to energy and it will disappear. But that doesn't happen, and we don't see the trace of antimatter. So there must be some physics behind it. Why there is no antimatter? What is matter like within the first few seconds of Big Bang? Hopefully, you have heard the first talk in this program, and you might have got some idea, but we'll not touch upon that thing. The most embarrassing situation in science today is that the almost all, like 95% of the total energy budget of the universe is not known to us. So we do not know what are the reasons behind it. Uh, Particle physics, astrophysics, and cosmology will try to answer these by collaborating with various other fields to push back the frontiers of knowledge. It brings to also it this area brings a lot of spin-offs. One of the most dramatic spin-offs that you see is the internet that we are using. All of us are 24 hours dependent on the internet. This is one of the spin-offs of this field. You go to any medical hospital, advanced hospitals, you will see lots of applications which are actually coming to this from this area. And there are many things. You go to airport security, and many other things are actually related and coming from this area. And it will continue to actually increase in this sector. Okay, to give a perspective, what I'm going to tell about my topic is very broad in that sense. And if you see what in the slide, you can see one side. It's actually I'm talking of the scale that I'm where we are associated with. The left-hand side is roughly, let's say, 10 to the minus 30 meter. When you go to a very small distance, let's say 10 to the minus 34 centimeter. So it could be like the Planck scale distance, where you have everything started from there, or you can go to the extreme end of the universe, like the universe dimension could be 10 to the power 30 cm. So that means the spectrum that I'm going to look at is roughly 10 to the power 60 orders of magnitude. So start with 10 to the power minus 30 to 10 to the power 30. So this is the order that I'm talking of. And during, if you look at the scale that we are talking of, you can see that at some point you have the Big Bang with the beginning, and then you have where these atoms, protons, these are created, and with the super microscope, so to say, Large Hadron Collider at Sun, which is actually probing to a distance like say 10 to the power minus 16 or 10 to the power minus 18 centimeters. So this is why these are called super microscopes. And if you come across, then you see that you have a human dimension. They all of us are in the meter, and then you have subsequently galaxies, etc., which are actually probed by various telescopes that have been mentioned here. So we are actually looking into all these aspects. In a sense, the study of big and small are very much related. One end, I saw the very smallest distance that's possible, and in the other end, I saw the largest distance possible. Are they related? Yes, maybe they are also related. You can see that the astrophysics and cosmology are the largest or the macro objects. And we also learned that the Big Bang is the kind of phenomena with which all these things started. And if you come to the other sector, for the smallest one with the micro level, you can say, of course, the micro is not literally correct because 10 to the minus 6, but what we are talking of is 10 to the minus 20 minus and beyond. So these are the smallest ones, and the today's standard model actually we established and we have understood most of these sectors. If you look at the bottom, there is a kind of cartoon which is called cosmic Ouroboros. You can see it's like a dragon kind of structure. If one way, if you see in the let's say clockwise, you can see you start with like 10 to the power 30, you go down 10 to the power 20 galactic structure, and then you come to like the meter structure, human dimension, you can say, and then you can go to smaller and smaller and smaller, and then finally you can see that you can connect it to. So in order to even understand the largest structures, you also need to know the smallest particles, so to say fundamental particles. So this is how they are related. Let me introduce a little bit about the particle physics, or say high energy physics that we talk of. The particle physics, the branch of physics that studies the smallest constituents of matter and radiation and interactions between them. It is also known as the high energy physics because many elementary particles do not occur in normal circumstances. Yeah? And you have to create them in artificially in some laboratories, and that's what we know. And also there is another way, like if you want to probe to smaller and smaller distance, then we have to go to smaller, higher and higher energy. In the next slide, I'll try to illustrate this point. To give a feeling like the study of structure of atoms, which is of the order of angstrom, we need an energy of keV, like 10 to the power 3 electron volt. And when you go to the nuclear structure, if you want to understand, then you have to have energy of the order of 10 to the power minus 10 to the power 6 electron volt, or MeV. And there you can actually decipher distance up to the level of Fermi. Then if you go beyond that, if you want to look at what is the structure inside the proton, roughly, let's say 10 to the power minus 3 Fermi, then you have to have energy something like GeV, or 10 to the power 9 electron volt. According to quantum mechanics, the d wavelength of a particle is roughly equal to h over p, that we all know h is the Planck constant, and p is the momentum associated with the particle. In order to understand the structure at a very small scale, we require probe of very small wavelength, and hence we need to go to higher and higher energy. So what are the tools involved? Of course, special relativity for very vast particles. We need these things. And then we have, you want to actually deal with the smallest possible particles, then you have to invoke quantum mechanics. And if you combine these two, then what is called the quantum field theory. And this is how roughly we can see that if you look at the cartoon, which is shown in the bottom, actually you start with world quantum theory. If you go down, actually, you can see that the classical mechanics and Lorentzian mechanics. Then if you actually go right hand side will be smaller, let's say. So if you go to smaller dimension, then you have to go quantum mechanics. And so the marriage of these two is like very fast moving particles and very small is very best actually described by quantum field theory. But then again, special relativity also will be modified by general relativity. That sector, if you actually combine with quantum mechanics, will be quantum gravity, which is not yet understood. So this is the open area if somebody is really interested in looking. So coming back to the point that I mentioned in the previous slide, if you can see that the microscope is a kind of a beginning of this kind of physics that we are talking of. As I mentioned in the previous slide, it is to probe wavelength, we should be smaller than the distance scale to be probed, and one can actually probe delta x equal to roughly h cross over e. Actually, that should be square root of e, is h over p. Let's say. Okay, so these are the various dimensions that we are talking of, and I think these things I have mentioned in the previous slide, so no need to go through again. We know that in the second quarter of the 20th century, we came to know that the proton and neutrons are together by the strong force. And in the third quarter, actually, we came to know that proton and neutrons are also found to be consist of still smaller objects known as quarks. And this is the cartoon which actually shows on the left hand side how the atomic structure we have. We have a nucleus which consists of neutron and proton, and electrons are surrounding the nucleus. And this is the length scale that we are talking of, which is actually shown on the right hand side. We can see that the smallest one are basically in comparison to the length dimension of, let's say, atom. These are actually, you can see the electron is 10 to the power minus 18, and also quarks will be of the similar order. So we are actually trying to probe distance to these small length scales. So when we talk of these fundamental particles, and we need to understand the interactions between them, and these are the ones we are we are familiar with. There are 4 interactions: the strong interaction, electromagnetic, weak and gravitational interaction. These are the 4 interactions involved. And if you look at in the table, the first column gives all the interactions that we have: strong, electromagnetic, weak, and gravitational interactions. If you want to compare their strength of all these 4 interactions, which is actually mentioned in the second column, by definition, we start with strong interaction to make it normalized to just you start with 1. Whatever is the strength for strong interaction is 1. In comparison to strong interaction, we have electromagnetic interaction, which is 10 to the minus 2, and weak interaction is 10 to the minus 5. And in the same scale, the gravitation is minus 38. So you can see that whenever we talk of strong interaction, or for that matter, electromagnetic and weak interaction, we see that gravitation has no role to play. Similarly, if you look at what kind of range they are associated with, these are like strong force and weak force. They are very short range. And we know that electromagnetic is infinite, and gravitation is, of course, a very long, so to say, infinite range. The exchange particles are actually, these are quantum mechanical interpretations of the force. Whenever there is a force, all these force, strong, electromagnetic, weak, and gravitation, then we, from quantum mechanics, we understood that there has to be, this is a quantum mechanical explanation of this interaction force, that there has to be some kind of a fundamental particle exchange between these forces. In case of strong, we have the gluons, and in the electromagnetic, we have photon. Then in weak interaction, we have the 3 bosons named W plus, W minus, and G boson. And similarly, it is believed that in case of gravitation, there has to be some kind of a fundamental particle which could be graviton, which is not yet found. Okay, and these are the right hand side. I have given some kind of a particle which are experiencing this kind of force. This is the summary of so to say, standard model of elementary particles. What we know today is there are 3 families of quarks and leptons. So in the first part, in the top row, you can see that you have up quark, down quark, top quark, and then there are corresponding anti-quarks like anti-up, anti-charm, and so on. Similarly, in the second row, you can see down quark, strange quark, bottom quark, and corresponding the anti-quarks of anti-down, anti-strange, and anti-bottom. The third row actually consists of electron, muon, tau, and the corresponding antiparticle, positron, anti-muon, anti-tau. The last row consists of these 3 neutrinos and the corresponding anti-neutrinos. These are really the mysterious particles, and you will come to know more about these during this program, maybe during the next 2 days. On the right hand side, you have all these bosons, the interacting intermediate particles, which are actually responsible for the various forces that I mentioned: gluon, photon, G boson, W boson, etc. And ultimately the Higgs boson, which is also responsible for giving mass to all the particles, which was actually discovered in 2012. So finally, we are actually in a stage we have completely more or less understood the standard model of particle physics. But there are many things that we don't understand. As we progress, we'll see that there are many anomalies that we do not understand. For example, the neutrinos in this standard model were found to be initially assumed to be in standard model to be massless particles, but what we have seen these days is they are not massless particles. They do have mass, and they do oscillate among themselves. So this is one, and we'll see that there is evidence of dark matter, which is also not understood with the basis of standard model of particle physics. So we need to actually go beyond the standard model to understand a little bit more. Okay, I'll leave that section here and then try to actually motivate a little bit about the variant asymmetry of the universe that I mentioned at the beginning. So why there is matter dominance? The early universe was devoid of matter. As the universe expands, matter was able to form for the photon-proton interaction going to particle-antiparticle. The naive understanding of Big Bang says that there was equal amount of matter and antimatter to begin with. In the at the beginning, that means there is a symmetry between matter and antimatter. Equal amount of matter and equal amount of antimatter are created out of the photon, let's say photon plus photon energy. If that is the case, then where is the trace of antimatter? In which place we can find that? Of course, artificially we can create antimatter, and we know that the anti-particle of electron is positron, which is which is used in one of the sophisticated diagnostic tests. It's called positron emission tomography. Some of you might have known, and these are used in medical sciences. So we can use artificially create antimatter and use for various purposes. But having said that, normally we don't see antimatter. Hello, is there any? In 1967, Sakharov proposed that this surplus of matter is possible only if one of the forces violate matter-antimatter, namely the the C parity or CP violating processes. These are the there's some sound. Okay. So there has to be some kind of a violation of C or CP. C is charge conjugation of quantum number, and P is the parity. If you have a violation of C and CP, this is one of the reasons. And baryon number must be violated. Baryon number is associated with are given to these quantum numbers are given to various particles, and so far we have not seen any baryon number violation. Maybe at some point the proton decay. If you see proton decay, proton is supposed to be stable particle. If you see that proton decays, and then we can see that there is a violation of baryon number. By the way, let me also emphasize that there are two great physicists from Odisha, Professor Satpathy and Professor MOHAPATRA. These are the two great scientists who have worked a lot of things related to baryon number violation. So the third one is there must be a thermodynamic non-equilibrium, and that is also that's one of the conditions, but the most important one is basically CP violation is the most important gradient if you want to have a variant asymmetry of the universe. Okay, this cartoon I will not say. Matter dominance of the universe, it is one of the greatest puzzles. So far we have not completely understood. The observable universe reveals a clear dominance of matter. If the moon were composed of, just to give an example, if the moon were composed of antimatter, the lunar probes and then astronaut would have vanished in a fireball, but that didn't happen. They went and then came back. So we know that moon also doesn't consist of antimatter. We also get the solar winds and cosmic rays. They are actually continuously bombarding the Earth, and obviously they do not destroy us. That means that they are also not antimatter. Sun and Milky Ways are also made up of matter, so we are sure that they are also. But then where is those antimatter? That's a question. Cosmic microwave background suggests that there is no region of antimatter within at least 10 billion light years, and perhaps the better part of the universe, but it must be still somewhere where it is basically. If you look at this cartoon, if you have matter and antimatter, if you just combine them, then obviously they will annihilate to energy, but we are not able to see this. The variant asymmetry of the universe, what we see today is actually given in this kind of cartoon. If you want to weigh the matter and antimatter, you can see that one side is completely matter and the other side is totally empty. You don't have the trace of antimatter. Maybe a little bit about CP violation. So CP symmetry, C is one symmetry, as I mentioned, C quantum number, charge conjugation quantum number. So it changes particle to antiparticle, and the parity symmetry, where the mirror symmetry, all of us are associated. We are familiar with the in quantum mechanics. So if you combine these two symmetry, this what is called the CP symmetry, and under parity, I'll not go through it. So the parity, if you have P of R going to minus R, which is the mirror reflection. So under parity, a left-handed particle transposed to a right-handed particle. And parity is conserved in strong and electromagnetic attraction, but it is violated in weak attraction. And same thing also, C is violated. And we have when we look at the standard model of particle physics, as we mentioned in one of the slides, there are 6 quarks. And these 6 quarks are actually, they are massive particle, and they have like weak state and mass eigenstate. They are actually related by so-called CKM matrix. This is CKM is named after 3 scientists, Kebibo, Kobayashi, and Moscow. They actually propose that there will be some kind of a like relation between the mass eigenstate and the weak eigenstate, and they are related by this 3 cross 3 CKM matrix. And so this phenomena actually can explain CP violation in the standard model. And that's what I'm actually trying to emphasize. So this matrix 3 cross 3 matrix that I wrote in the previous slide, actually in some parameter space, one can actually, using some kind of parameterization, one can actually express this. Let's not go into the details of it, but just to point out that one can actually assign some kind of a phase to one of the elements, which will give rise to CP violation. Okay, and this is next one I'll omit. Okay, so before going to the next section, let me just say that the CP violation has been observed in the V factories, and we know what kind of CP violation the standard model will actually give us. Unfortunately, the standard model, whatever CP violation will find, is not enough to match the kind of the variant asymmetry that we have seen so far. So, to conclude this portion, to say that standard model CP violation is not enough to explain the variant asymmetry of the universe. What people are looking at is right now they are actually looking at to the neutrinos. Maybe there will be leptonic CP. This was in the quark sector that I mentioned. Maybe there will be some kind of evidences from the leptonic sector. So we have not been able to measure the CP violation in the leptonic sector. There are various experiments going on all over the world to find out this CP violation. Hopefully, at some point, we'll be able to measure this CP violation in the leptonic sector, and we'll see how much it can contribute to the variant asymmetry of the universe. Okay, let me go to the next portion. Yeah. So this is one plot where actually we have the rotation curve of the solar system. As you can see in the plot, we have in the y-axis we have orbital velocity, let's say v written in kilometers per second, and in the x-axis you can see the radius r in terms of astronomical units, and various you can see like in the graph you have Mercury, Venus, Earth, Mars, etc., and up to Pluto. You can see that their orbital velocities are actually following a pattern which is basically based on the universal gravitational law all of us are familiar with. So if you start with the gravitation law of gravitation, we can simply say that V equal to root over of Gm over R. So if you look at they are actually completely following the orbital velocity as far as the solar system is concerned. Okay, so everything is working fine, and all of us are very much familiar that all the satellites and all these things are based on these principles. Everything is working fine. We have our networks, everything. But having said that, there are also certain other things which will give us the clue. Let's see what it is. Now, similarly, this was the previous one was rotation curve for the solar system. But now, if you go to the little bit length scale, if you increase, if you go to the galactic scale, let's say, you go beyond the solar system. Now, the problem with galaxy rotation curves, the outer stars in the galaxies do not rotate correctly. The outer stars should behave much like the planets of our solar system, as we saw in the previous slide. That's what the expectation is. But what we found is basically from various, this is one such experiment. There are many such experiments in which we actually found the similar kind of pattern. Let's look at this one, which is in the written in the, which is shown in the bottom. You say rotation speed, again it's a kilometer per second in the y-axis. Let's say we have some given units, 100, 200 and 300 kilometer per second. And then now the distance is now in kiloparsec. Kiloparsec is very large distance. Parsec is like 3.26 light year. So you can imagine like it's a very big scale that we are talking of. Now, if you see that in the graph, the red one, reddish kind of graph, which is becoming more or less constant from say 15 kiloparsec onward. But actually, if you follow the relation v square equal to, which is written in the right hand side, gm over gm r over r. So if you follow this law, then we should that this black dotted line is should be the one. It should follow the same kind of pattern, which is actually depicted in the dotted black curve. But unfortunately, what we see in experiments is more or less the velocity remains constant, which is really like a kind of a surprise for all of us. On what basis the orbital velocities are actually becoming like more or less constant. So let's look at the right hand side equation. If you see that the v square is roughly constant, but in the equation, if you follow Newtonian gravity, then we see that it should be 1 over r, right? So if you want to make it constant, g is a law of gravitational constant and mass of the system that we are talking of. And if you want it to be constant, then let's say these are the only things that were associated with. So if I put mass is directly proportional to the radius or the length scale r, then you can see that r cancels and you have something like the v square is constant. So that means whenever you are talking of the galactic system, whenever you have a large system that you are considering, they are actually, we see that the mass, the total mass associated with it is roughly proportional to the distance, which is against our understanding that we should say that mass should decrease when you go down. And that means there is something which is actually there, but it is not visible. So to the visible sector was the one that I actually mentioned at the beginning, the quarks, leptons, and all this galactic thing that we can explain out of it. That is the visible sector. And the visible sector, whatever we expect, we are seeing it, but unfortunately, there is something very much hidden somewhere, which is not showing up to the visible sector, and this is what is called dark matter. So if there will be dark matter, then it's possible that we are not able to notice it, but it is still there and it is contributing to the gravitation. So this is the kind of cartoon that we have. You can see that the galactic center, you have something like that, the center, but it is actually forwarded. It is in a kind of a medium where you have, there will be some kind of a dark matter halo. So everything is inside this halo. So, but we are not able to see it, and still they are contributing to this. So this is just a cartoon. So dark matter, by the way, we have, as I mentioned, that that will not be part of the particles that already I shown you. This quarks and leptons, all these particles, they will not account for the dark matter. So somebody has to, we need to go to beyond the standard matter. There are many theories where you can have dark matter contents, but so far we have not seen any trace of any dark matter. So there are many experiments going on to find out what the nature of the dark matter and what consists of dark matter also. Okay. For example, supersymmetry was a beautiful theory which was actually constructed a few decades ago. There are candidates which can actually give rise to dark matter, but we have not been able to see any trace of supersymmetry, or for that matter, any other theory which actually can give rise to this kind of dark matter. So this is a dark sector. That's what Just to introduce what is this that I mentioned at the beginning. If you remember, I said that 95% of the energy of the total universe is completely dark, and we do not understand. So this is the cartoon. The latest one is actually found from WMAP satellite experiment. Let's say you have this is kind of a cosmic pie. You have the total energy budget of the universe is, let's say, 100. If you look at this, then you can see that whatever we know or the visible sector is something like roughly 5%. The atoms and everything that we have described so far consist of only 5%. And the green portion, as you can see, this is dark matter, roughly 24 or 25%, and which was just like I explained that we have seen this rotation curves behaving like a velocity going more or less constant for the outermost stars, which is actually constituting, which is actually responsible for this kind of dark matter. Similarly, the rest one is actually roughly 70% is what is called dark energy. So that means if you sum up, then you see that there is roughly 95% of the total energy budget of the universe is completely dark sector, which we need to understand why is it so. Okay, so this slide you might have seen already, but just to give you some perspective, we start with some kind of a big bang at the beginning where the universe was created, and there is a phase of inflation where the quantum fluctuations were there, and it rapidly expanded from a very small scale to very big ones, and then it kept on. So you can see that this is the like greenish one that we are actually seeing through the cosmic microwave background radiations, and then we have the various other things which started after that, which is basically all the galaxies formed, and you can see that if you start from roughly from the beginning, and we are roughly like 13.7 billion years, not being very precise. So this is what is called the Big Bang expansion, and you can see the right hand side is where we are, basically most right portion. We believe that we are in a stage where it's actually dominated by dark energy, or it is not just being expanded, the universe, it is actually accelerating also. So the universe is expanding and also accelerating. So this is another cartoon to show that if you start with like, let's say we are here at the bottom somewhere and we are trying to look beyond to what we can see. So the best thing is like we are seeing these photons basically. The photons actually come from the surface of last scattering. From there, these photons are traveling to us. You can imagine kind of a spherical kind of an enclosure. So the surface of the last scattering from where they have actually started moving, and they are actually reaching us, let's say. So if you look beyond, if you look in the opposite direction, we are actually able to see light from which it is coming. Beyond that, we cannot see it. So if you look at this is, I'm talking of the middle figure. And if you look at the left side, you can see that where actually we are, let's say about 13.7 billion years after the Big Bang. So when we are trying to look forward, then we actually have to go through these phases of CMB last scattering, then radiation, matter, energy era, then and go to the final Big Bang area. So Big Bang era. So that is what we are trying to see, and there are various experiments, including this LSC experiment. They are actually trying to go to as close as possible to the early universe to get some insight. Here, I should also mention that there will be some the particles that I mentioned at the beginning. The neutrinos are very crucial to understand this scalar structure. Hopefully, you'll learn a little bit more in the neutrino talks. The beauty part in the right hand side, you can see that whatever we are seeing that the spectrum of cosmic microwave background is actually giving, so the photon the background due to this CMB radiation, what we actually find is temperature is like 2.7 degree Kelvin with very good accuracy. You can see that error bar is like 0.001 Kelvin. And this actually nicely forms a kind of a Planckian structure, which is a beautiful thing. And so we wanted to, so we understand a little bit about the cosmic microwave background. This one is again the same plot, but just to emphasize that how precisely we have measured this temperature. the uncertainties are actually multiplied 400 times actual uncertainty, just to show you that they are how accurately measured. Anyway, nothing to spend time on that. Coming back to one of these stats, let me go back to this one. You can actually look at the CMB spectrum from where actually it started. So you can see that the left-hand side plot, actually, you have Thomson scattering between various electrons, and then you have the nucleus also in this medium. But let's say in the middle where it is written last scattering surface, where atom and this nucleus, the atomic structure forms, and then there is no more interaction. And the photons actually start from there itself. And so they are starting from there, which is a last scattering surface, and they are coming to us. We have detected them. These are basically the cosmic microwave background radiations, which are detected with 2.7 degree Kelvin. Similarly, their efforts are on also to find out the cosmic neutrino background. These are the two the seeds of galaxy formation from early anisotropic temperature. You can see these are the two pictures that we have actually obtained of the universe that we have. The first one is a very old one. It's a Covey satellite picture where you don't see very clearly, but with the latest one, WMAP satellite, you can see the temperature fluctuations, which is an important area of research, and many people are involved to understand these fluctuations. Will give us a lot of information about the early universe. Let's come to the last portion of the talk. So here we will say that when we see the universe starting from the Big Bang, in the left hand side there is a plot. Again, it is velocity in kilometer versus the distance, and all these you can objects you can see here. Maybe I have another one. You can see that this is what the galactic velocities. You can see that left hand side is velocity kilometer per second, and in the right hand side you have distance in megaparsec. It is megaparsec, not in even kiloparsec. It's a very far distance, and you can see that all of this is like a plot of 1355 galactics. You can see that they are basically the velocity versus distance is roughly like they are linear relation. Okay, so let me come back to this one. You can see that this was due to Edwin Hubble, who actually found that the velocity and the distance are very much linearly proportional, and that proportionality constant is what is called the Hubble constant, and we know the value of Hubble constant today. And there is a little bit of confusion regarding this. The current research is concerned. People are trying to fix that. There is some mismatch with whatever we have seen and what the theory is giving. But anyway, there is a different area of research. More or less, this is what the Hubble law says, that the velocity is directly proportional to the distance between the galaxy and the observer. So universe started with a hot plasma, Big Bang, as we already know, and we have from the nucleosynthesis, we have understood correctly the helium-3, the deuterium, helium for alpha, lithium, all components are very well understood. So the Big Bang theory that we are actually studying is able to understand the light elements we see. And of course, as I mentioned, this photon decoupling from the thermal bath led to the cosmic microwave background, which has been already here. Actually, just two things that we actually use a lot of response. For example, redshift is defined this way, and this is the Hubble law that I have given. Okay. So now there will be, okay, maybe I have, yeah, so I'll come back to this later on. Okay, so here the basic principle that in cosmology that we are using is basically we are using the homogeneous and isotropic universe. We have the universe is homogeneous and isotropic. So using those principles, we have something called the basic equation that we use in the cosmology is basically Friedman equations. So H is basically A dot over A. So A is what is called a scale factor. So let me go back to the previous one. No, sorry, next one. Yeah. So this is like you imagine a kind of a mess which is there at the bottom, and let's say the universe is expanding. You can imagine like all the galaxies are in some of these like joints, some cross points. You can identify some kind of a lattice that the galaxies are actually situated in this kind of lattice, let's say, and you expand the mesh. So the mesh is expanding, that means the space is expanding, but the galaxies are there in that position. So time arrow is written on the upward, as you can see that with time how this space is expanding, and this is best represented by so-called the scale factor A that I actually mentioned in this previous one. So you have the scale factor which is A, and the time derivative of scale factor A dot over A is simply called the Happel constant H, and H square equal to simply, so we'll not derive any equation here. This is what is called Friedman equation, which is very famous. And you have the H square is 8 pi G, G is the gravitational constant, and rho is the density. And then we have introduced something called K over A square. K is something which is actually written in the previous slide. I'll come back to the curvature, and divided by scale factor square. Okay. And similarly, we can also find out the acceleration equation, A double dot equal to A. And this kind of equation we can find. This is pressure basically, and pressure will have a minus rho of dark energy density. So I'll come, and I'll come to this towards the end. So if you see that what we find from various experiments, this acceleration is actually positive, and that means the universe is not just expanding; it is actually accelerating. So coming back to this slide, so far what is called the standard model of cosmology is what is called lambda CDM, or lambda called lambda is cosmological constant. So, and it is actually best describing what is called a flat universe. So depending upon the geometry that we are talking of, I'll come back to that a little bit towards the end. So the curvature that I just mentioned, depending upon the curvature, what kind of curvature that we are considering, you can see that the universe could be open universe. It could be like this. There are three possibilities that I have mentioned in the left plot. One is called open universe. The other one is flat universe, where I can take k equal to simply 0, which is flat. And it could be like k is greater than 0, less than 0, it could be closed universe. So what the lambda CDM or the standard cosmological model is more or less preferring so-called the flat universe, where the curvature equal to 0. And these are the right hand side some various curvatures that we have given, like the flat universe, then closed universe, and then the open universe. The first one is closed, and the middle one is open, and the third one, the bottom one is the flat universe that we are talking of. Fortunately, the observations that we have actually is representing the flat universe. This one I have already explained. Okay, yeah, I have this plot again. So here you can see this k that I wrote here. This k is the curvature that I'm talking of. Depending upon the various k's, you can have a closed universe, you can have an open universe. K is less than 0 is open universe, k is greater than 0 is closed universe, or k equal to 0. You can see the same equation that I wrote before, which is written on the right hand side at the bottom. So h square equal to 8 pi g over 3 into rho minus k over s square. So when you take k equal to 0, obviously you are left with only the first term, which is actually corresponds to the flat universe, which best describes the data right now. So this is another way. You can see that people have actually found that universe is actually accelerating. You can see in this plot what we have. If it is decelerating, what we have plotted here, scale of the universe or scale factor A versus the time that you can see in the x-axis. So if the universe is accelerating, then it will have something like going upward. If it is decelerating, then it should have negative acceleration, which will go this way. But from the various experiments that we have found so far, we see that it is tend to be accelerating, and for this people have actually got Nobel Prize, almost a decade ago. So we know that right now the universe is expanding, and also it is accelerating. Okay, so this is one just to begin with the Big Bang. Let's say you start with radiation, and the terminology that I introduced sometime back, the scale factor. One can actually find out the density of radiation, which is in the right hand side. You can see it goes at 1/a to the power 4. A is the scale factor that I wrote. So as A expands, that you can see that it is actually become less dominant, because you can see that the matter density varies as 1/a cube. So if you start with the y-axis is actually density plotted in log scales, and the x-axis is time plotted log time. And you can see that if you start with, let's say, radiation, we know that it starts with radiation because it started with a big bang with a lot of energy radiation will be there. So we see that it varies as 1/a4. So with time, actually, the radiation becomes less dominant. And at some point, you can actually consider at some point the dotted one, which actually represents the matter density, which varies as 1/a cube, and this becomes dominant. So as we progress in time from the Big Bang onwards, we see that after some time there is a crossover, and the radiation-dominated universe is actually replaced by matter-dominated universe. So matter-dominated universe is where you have all these matter-created proton, neutrons, and galaxies, etc., etc. So earlier it used to be radiation-dominated, and at some point, maybe 3 million, 3 billion, 4 billion years ago, it actually started becoming the matter-dominated. So if that is the case, then what happens? But what we found is that there is another contribution which is coming from the vacuum energy or the vacuum energy density. So if you see that, if I can actually add next one, you can see there is some kind of a constant vacuum energy. Let me put it as a constant line. So the density is, let's say, constant with respect to the scale factor. So it will not be affected whether scale factor is increasing or decreasing. Now we can see that whenever the time is very small, then the vacuum energy has no value. It was earlier dominated by radiation. After some time, it became the matter dominated. But then again, it also goes 1/aq. When the scale factor increases, it will again come down. But if you see that the constant term, which was earlier very less, but after some time, it actually surpasses the matter dominated universe. So you can see that at some point it will be related, it will be dominated by the vacuum energy or the cosmological constant dominated or dark energy dominated universe. So that's what the region in which we are living. So this will actually lead to the acceleration of the universe, and the universe is actually in this kind of phase right now. So this is a cartoon. You can see that there is some leftover old electric engine where you can see some mathematical equation. Those who are familiar with gravitation and cosmology, you can see that Einstein's field equation is written here: R mu nu minus half G mu nu R equal to minus 8 pi G C4 over T mu nu. Okay, let's not go. So this used to be the original equation, but there was some change. So let me start with the Friedman equation that I mentioned some time ago. The Friedman equation in the presence of cosmological constants. So if you look at the first equation, I used to have h square equal to 8 pi g by 3 into rho minus k over s square. The third term was not there. But let's introduce the cosmological constant, which actually in the previous slide I mentioned that you have. So this is kind of a vacuum energy, which is a very constant term that I have added here. Let's say lambda over 3. So you can see that ultimately, if lambda becomes positive with time, that will be giving rise to a positive acceleration. Okay, so that is the so-called cosmological constant. One can actually, yes, include in the Einstein's field equation, and actually Einstein added this cosmological term to his famous equation to make the universe static. And then later on, he realized that maybe he did some mistake. But the last couple of decades, we actually come to know that this is actually explaining the accelerating universe, which appears to be perfectly fit with the time. Okay, so I'll not go into are some technical aspects. So we have the nature of the dark energy, the cosmological constant, first invented by Einstein in 1917, and but the unfortunate part is this lambda is very small, like 10 to the power minus 20, 120 Planck to the power 4. And one can actually find out, can start with some kind of scalar field Lagrangian, half Python square, and find out that the pressure will be like minus 1/3, which will actually explain the dark energy problem that we are talking about. Okay, I'll not spend more time, but there are ways to look at it in the sense that one can actually modify the Einstein gravity, what is called modified gravity. There are a lot of people working in this area to understand the dark energy and various other aspects of physics that we are actually observing. Some of these things are mentioned here. So I will conclude with this, with my outlook, because it's already lunchtime. Standard model of particle physics looks to be complete. We have actually found all the ingredients, and it is perfect, or there is no violation of prediction with whatever prediction we have made the prediction over the last few decades. So that is a complete theory right now, but nevertheless, it is not able to explain some of the observations in the universe. For example, neutrinos, dark matter, dark energy, and many other things. And so there must be physics beyond the standard model, but we don't know what exactly. So far, with despite our lot of efforts, we didn't see any evidence of physics beyond the standard model. We have seen evidence of neutrino mass and dark matter, so we need to explain all of them with certain kind of theory. Dark energy is actually giving rise to this cosmic acceleration, so we need to understand this, although there are some kind of a work in this, but it is not correctly understood. It's an open field. We have not been able to quantize gravity, which is one of the important problems facing in this area. So people are working for maybe last 100 years or so, let's say, since quantum mechanics was invented. So it's an exciting time in this field, and thank you for your kind attention. Thank you very much.
Thank you, sir, for such an interesting and nice talk. I'm sure it will definitely benefit our students. Now, we have a few questions from the participants. The first question is, during the creation of universe, if equal number of baryons and antibaryons were created, then what led to the baryons dominate and not leading to complete annihilation of particles?
Just go back to the slide. So can you read again, please?
Yes, sir. During the creation of universe, if equal number of baryons and antibaryons were created, then what led to baryons dominate and not leading to complete annihilation of particles?
So it started from the, like, if you know the any collision process, so how do you go to back, right? It immediately, if it is created particle antiparticle, how they will combine. Of course, if you force them to combine, obviously it will be. For example, you bring, like, say, proton and antiproton together, or particle antiparticle, electron and positron together, then only it will actually annihilate to become energy. For example, let's say I'll give you, is it possible? So you have to have that kind of scenario possible, and they should be in contact. Okay. So when they are actually going back to back, or whatever possible, for example, you have energy, if gamma plus gamma, as you can see in the slide, it is written, the particle and antiparticle are produced. Once they will come in contact, then only they will form the energy. And if you see, then energy itself only, you don't see baryons or antibaryons. But what we see is only baryons. We don't see antibaryons. So there must be some other physics principle behind it. And that's what people are found that these are the three conditions so far we have understood. And hopefully CP violation is the main culprit behind it, apart from the thermal non-equilibrium and baryon number violation. So CP violation should be able to give us. And if standard model is not able to give us any source which can explain the baryon asymmetry of the universe, which is of the order of 10 to the power minus 10, like now, maybe there will be some beyond the standard model which will give us some kind of a clue why it is there.
So, the next question is, what is the dark matter composed of? Is it the atoms, molecules, or something else which is not discovered yet?
Yes, exactly. Very good. So as I mentioned, I think I mentioned previously also, these are the particles that we know so far. Okay, all of them we have seen. And this consists of standard model, and this consists of all the particles or baryons that we know. But there are other models, like there are duplicate supersymmetry. There will be an equal count of whatever particle that you are seeing. There will be corresponding supersymmetric particles also in the theory. But that's a theory. We have not seen that theory. So we believe that if at all tomorrow there will be dark matter discovery, we will find a new kind of particle maybe. So it is quite likely that none of them, in fact, so far we have not found anything. So the dark matter will not be part of whatever we have seen so far. This is actually the visible universe, which roughly consists of 5% of the universe. Okay, so it has to be a different set of particles, which we don't know what exactly. So this is an open field. Many people all over the world, all over the world, are trying. So I think it's an interesting area to find out what exactly it will be. Nobody knows. No idea.
Okay, sir. The next question is, why do we include the phenomenon of quantum fluctuation to dark energy or dark matter? Because quantum mechanics is associated with atoms or molecules.
No, first of all, this is one area where quantum mechanics is not yet included. Okay, so the dark matter, there might be some quantum physics, but the dark energy that we have is completely classical. There is no quantum physics associated. If you just look at the quantum fluctuations which are at the beginning of this, then there is quantum mechanics involved, but that is not correctly understood yet. So this part of the last part of the talk that I mentioned about dark energy, it is purely classical. And as I mentioned that we have not been able to understand the gravity, the quantum aspects of gravity, which is, there are four interactions I mentioned at the beginning that if you remember, one is called electromagnetism, then you have strong, and then what more? There are weak, strong, and electromagnetism. All these three we have understood in the framework of quantum mechanics. This is what standard model is all about. But the last one, the gravity, is not understood using quantum mechanics. So that is the idea of quantum gravity when you actually use the mechanism or the principles of quantum mechanics. But that is an area work in progress. So I think it's a challenging area. Many people have tried for many decades since 1930s or so. But so far it is not understood. So there is no direct relation right now to that sector.
Yes, sir. The next question is, when we say that the universe started with hot plasma, then how is the dark matter created from this plasma?
First of all, we don't know at which state it is created. So if you look at the cartoon that we have shown many times, let me just go back to one of the cartoons. Let's say this one. Let's say, so which age actually dark matter is consist of, started or created, or what consists of dark matter? Nobody knows right now. So that is a complete mystery. But what we see from the observation, that there must be something which is not visible, and it is called dark matter. The nature and behavior of the dark matter is completely unknown. So anybody who can give should get a Nobel Prize. And the same is true with quantum gravity and dark energy. There's a lot of things that we don't know. So the nature of dark matter is completely unknown. So we cannot say anything about, although we believe that it should be interacting with gravity. That is the only way that we want to do some experiments and try to get some insights into the dark matter. But whether it is created inside the hot plasma, which is quite unlikely, I think that is not yet understood.
So the next question is, what are the possible candidates of dark matter?
Yeah, there are many possible. There are supersymmetric particles. Lightest supersymmetric particle is supposed to be the dark matter. We have something like WIMP. For many decades, people are actually working weakly interacting acid particles. These are actually the strong candidates of dark matter. Neutrinos at some point were considered to be dark matter, but that was supposed to be hot dark matter, but hot dark matter is completely ruled out. We have like a cold dark matter. So neutrino is almost kind of ruled out unless and until it is a moderate dark matter. So there are various BSM physics people have actually proposed. Looks like the axion-like particle. Axion is also could be kind of a dark matter particles. So there are many particle candidates which could be like the dark matter candidate, but they are coming beyond the standard model, as I said again. So these are some of the possible candidates for dark matter.
Next question is, does the expansion scale factor obey the Taylor series?
No. It has nothing to do with the scalar Taylor series, basically.
Yes, sir. The next question is, what is the relation between singularity and Big Bang theory? What if the universe stops expanding?
What is the universe?
What if the universe stops expanding?
What if universe stop expanding? Maybe it will collapse. There are three possibilities I think we have mentioned, right? We don't know actually, but as of now, at least we can say that it looks like flat. So if it is k is less than 0, the curvature that I am talking of, it will be an open universe that I saw the hyperbolic surface. But it can be a crunch, like it can collapse to the same thing, which is basically you can see that k greater than 0, it will be crunch kind of thing. The way you have a big bang, it will be a big crunch, something like that. But we don't know. I mean, we have actually come through like 13.7 billion years, so nobody knows. The universe is now, if you look at this phase, basically, you can see that we are actually accelerating and it is going upward. But it's quite unlikely. At least we cannot see on our eyes, but it may be possible. We don't know. There are modified Newtonian gravity theories. They are actually this kind of phenomena are still considered. In any case, these are open fields. I mean, nothing is clearly understood. And if you can formulate a theory and you can explain, maybe it is possible.
So what is the relation between singularity and Big Bang theory?
Singularity and Big Bang theory, I don't think there is any relation. We said that it's starting from Big Bang, some kind of an explosion, but it could be from a singularity, it could be something else, nobody knows basically. So as far as I know, I think we don't have anything, but I would recommend that you can actually ask this question to the person, the faculty member who is going to speak about quark-gluon plasma or Big Bang theory. But as far as I know, I don't think there is any direct relation with the singularity.
Is dark matter related to black hole?
One can be, yes, there is a possibility that it could be there. It could consist of, people are trying to actually explain that. There are a lot of ideas people have, but yes, it is possible. This is one of the possible places where dark matter could be hiding.
Sir, if dark matter is dark and doesn't interact measurably with matter or give off light, how do we know it's there?
Exactly. That is the beauty of this subject. Yes, as I said, like it doesn't interact with the visible sector. Otherwise, we have been able to see it. So that's what it will interact, but it has mass, so it will interact gravitationally. And that's what we are trying to do. We are using different types of like gravitational interactions and some indirect method to find out the. It's not so easy. Otherwise, people would have found if it is there for despite their like efforts for a few decades, we are not able to. But yes, it will interact gravitationally, and that is what we are trying to do. It will interact through gravity. Indirect way, we'll try to get the signature.
If there are multiple universes, then
Yes.
can we say that there is more dark matter present in those universes?
Yes, multiverse theory is like a very popular theory these days. People are telling of there are multiverse universes. It is called the name is called multiverse. It's a very popular theory, and people are talking a lot in the last few years. It's possible because we don't know about one universe, so it's very difficult to say about multiverse. But anything is possible.
So the next question is dark matter there to counter the presence of all the celestial bodies present in the universe?
Sorry, I couldn't hear.
Is dark matter there to counter the presence of all the celestial bodies present in the universe?
I don't know what is the meaning of this question, but if I understand, the dark matter is actually giving us that kind of additional matter content, which is evidenced by the rotational velocity of this galaxy that we have found. But how it will counter of course, even if it is, let's say you violate the gravitational law at large distance, maybe there will be something. You can actually look into the modified theory of gravity. One can actually consider these kind of ideas, but I'm not sure.
So the next question is, what is the scale of this vacuum energy? And can we say that everything has originated from vacuum? If yes, then did Big Bang occur inside the vacuum?
No, you start with the vacuum. Everything started from vacuum, right? So you start from somewhere. So what it has from where it has started, we cannot say right now. Obviously, it has started from somewhere from some kind of a fluctuation, but it is not correctly understood. This Big Bang scenario, basically. But we believe that this is what it is. It's not correctly understood. But that's what many experiments are trying to do, that all these LSC related experiments and many other experiments, we're trying to gather information what could have happened during that point. That is the whole idea of it. I mean, if somebody knows, then there is no point in doing this experiment and try to learn. Yes, it is not very well known, but yes, that's all.
Yes, sir. The last question is, what are the merits and demerits of universe expansion? Is it possible that sun may drift apart from Earth due to universe expansion?
Yeah, it's a beautiful question. If that is the case, then we'll die soon. If the sun, so obviously this, okay, I think this should be, this is the very crucial point. As I said, like these are like, this expansion is actually noticed very, very, very large distance. So for sure, with the like universe is expanding, you cannot say that distance between like Bhubaneswar and Delhi is going to increase. It is not the case. So unfortunately, this is not. So there is no distance change going to happen with the sun and us. So otherwise, you will get less radiation and the temperature will cool down and maybe you will die sometime soon. That is not the case. So the universe is, so the distance between the sun and us is not going to decrease or increase. Sorry, expansion. Yeah. That is
So we have another question. Is it possible to explore dark matter using gravitational lensing?
Yeah, that is what we are getting. We are actually getting evidences through gravitational lensing. As I said, like it is actually gravity will give us some idea, and gravitational lensing is actually giving one of the. So I didn't actually give what are the other possible evidences of dark matter. Yes, gravitational lensing is one. So yes, we are using gravitational lensing for that. Sure.
Thank you, sir. On behalf of the Department of Physics, I thank you again for sharing your expertise with us and your time.
Thank
Thank
you.
you, sir.
Thank you very much. Thank you. Thank you.
Thank you, Anjan sir, for joining us.
Thank you. Thank you very much. Thank you. Thank you.
Good afternoon, sir. ଭଲ ଅଛନ୍ତି?
ହଁ ଭଲ ଅଛି।
ଆଚ୍ଛା, ଆଉ ଅଛି 2-3 ମିନିଟ୍ ଅଛି, ଷ୍ଟାର୍ଟ କରିବା।
ହଁ ମୁଁ ଟିକେ ଦେଖି ଦଉଛି କେମିତି
ହଁ,
ଆମେ ମୋ ଟକ୍ ଟା କେମିତି କରାଯାଏ ମୁଁ ଭୁଲି ଯାଇଛି।
ହଁ, ହଁ, ଆଜ୍ଞା, ହଉ।
Look, can you come here? Let us see why, how to my screen is not.
Yes, sir, screen is visible.
But I cannot see here. How I shall see? Or maybe I need to minimize it or what?
So screen is not visible.
To me, it is not visible. Let me see. Somebody can help.
To us also it is not visible.
To you also not visible?
No, not visible.
Sir, just minimize the browser.
Minimize the browser. I did that.
Yes. Now go to your PPT.
Go to my PPT, maximize it.
Okay. And this maximize it. Then full screen mode, sir. Go to full screen mode.
Full screen means, yeah.
That is slideshow. Go to slideshow.
Yeah, I'm doing that.
Yes. No.
There's something.
Yes.
This is in full screen mode.
Yes. Now this is correct. Okay.
there is
Now it is full screen mode.
something is opening up. Let me. Now visible, na?
Yes, sir.
Very good. Just a minute. Okay. Where did it went? Switch off this one. Just a minute. What?
So good afternoon all to this afternoon session. Now the talk will be delivered by Professor Devakant Samal sir on topic emergent electronic phenomena induced by spin orbit coupling in solids. So to give a brief introduction about sir, I request Prachi madam, Dr. Prachi Mohanty madam, to give a introduction about sir, and then talk will start.
Welcome back to the second session of our webinar. A good afternoon to all of you. It is a great privilege to introduce our next speaker, Professor Devakant Samal from Institute of Physics, Bhubaneswar. Professor Samal is a very well-known physicist in the field of condensed matter physics. His research interest is mainly focused on the microscopic understanding of the emergence of novel electronic and magnetic phenomena in atomically engineered thin films or heterostructures and electronically promising bulk materials. To his credit, he has bagged several awards and grants. In addition, he has published numerous high-value articles in journals like Nature Communications, Scientific Reports, Physical Review B, Physical Review Materials, Europhysics Letters, American Physics Letters, Dalton Transactions, and Journal of Physical Chemistry, C, etc. Without wasting much of time, I would like to invite Professor Samal to enrich the audience from his vast experience. Sir, please.
Okay. Good afternoon, everyone. Thank you for this nice introduction. And first of all, I'd like to thank Bobita Madam, the organizer, for inviting me to deliver a talk on the topic that I have mentioned here, emergent electronic phenomena induced by spin orbit coupling in solids. This is a kind of this is a recent research work that people are mostly involved with. So I will try to give you a glimpse of what we have been doing and what is the role of spin orbit coupling in solids and how it can give rise to various emergent phenomena. So this work, mostly I will be presenting two of the results which are related to our research. And
Sorry, sir. Sir, is it possible to make full screen of your slide?
I'm doing that just a minute.
Okay,
Yeah,
thank you,
is
sir.
it okay?
Yes, sir.
Okay, so this is, I would like to acknowledge the people who are associated with me in doing some of our research related to the spin orbit coupling physics. So this is Subhati Vijana, who is a PhD student at IOP. And mostly I'll be talking one part of his thesis work. And yeah, Dr. Sachin Sharangi, who is a scientist here at the Institute of Physics, who is also associated with the research work. Then our collaborators from Niger, the Tapas Senapati, who is a student with Professor Karthik Senapati, and yeah, Karthik Senapati from Niger, who is associated with us in the transport measurements. And one of the work which I will also include in this talk is a work between collaboration between Professor Anil Kumar and myself here. And Mithun Ghosh is the student who was leading that project. I'll tell you what we have been doing in that project. And Shweta Bhatt is a inspired faculty at Indian Institute of Science, Bangalore. And of course, Professor Anil Kumar. I would like to thank the generous funding from Max Planck Partner Group and SCRB Government of India who are supporting us financially. That is why we are able to do this research. Okay, because there will be students, so let me introduce what is spin orbit coupling. So spin orbit coupling basically it is a relativistic effect, and we know that there is a nucleus and the electron is moving around the nucleus. This is in the real frame what we see. But if you see from the electrons moving frame of reference, then what you will see as if the nucleus is moving around the electron, and this is from the electron's point of view. So what it will realize, because of the, if you see it from an electron's point of view, and you can see as if the nucleus is moving around the electron, so because of this, there will be magnetic field induced, that is your B prime, which I have written here, and this is given by like this, which is comes from the Lorentzian transformation. So basically what we see is that because of this relativistic effect, the electrons experiences its magnetic field as B prime, and we know that electron has a spin. So an electron experiences a magnetic field and it has a spin. There is an interaction between the spin of the electron and the experienced magnetic field, that is B prime. So if you do this algebra, so this is basically, it is in textbooks. You can see that this spin orbit interaction, you do this B prime dot mu s. This is just like your Riemann energy, and you calculate it and you put it this, what is this mu s, you put it in terms of this Pauli matrices, and what you find is that the spin orbit coupling goes like this. This is sigma dot E cross P. So this is the generic form of spin orbit interaction, and it's a relativistic effect. And this is what I told you in the left-hand side figure. If you are just considering an isolated atom and the electron is moving. But in a solid, if you look at the array of these ions, and you have the electrons moving in an array of these ions. So here the spin orbit coupling is much complex, but the physics still holds good. So now what it has happened that the electron moving in the array of these ions, if you look at it from electron point of view, electron's reference point of view, so what you find that the electron also experiences a magnetic field, and that gives rise to what we know as the spin orbit coupling. And if you calculate the spin orbit coupling by taking the spherical potential, and you can find out that the spin orbit coupling generally it follows like I mean, this is the expression, and basically what I want to tell you that it scales with the z to the power 4. Z is your atomic number. So the spin orbit coupling scales with z to the power 4. Of course, it's z to the power 4 by divided by n cube, because you have En is here. So basically the spin orbit coupling, which is a relativistic effect that increases as you increase the atomic number or Z. That's why we call it the spin orbit coupling. Atomic spin orbit coupling is manifested more in heavy atoms, because in heavy atoms, you have higher value of a Z. And in a solid, this is one of the interactions, spin-orbit interaction. And in a solid, there are ranges of energies for various interaction. And if you can really, this is a good idea to know the range of the range of interaction energies for various interactions that's present in the solid. So I have put a scale here. In the top, you can see I have put various kind of interactions, and I have put what is their typical energy scales in the conventional materials. And I have also scaled it because energy always you can put it in a temperature scale. So you can find here that this is the spin-orbit interaction, the left-hand side, the top one is the spin-orbit interaction. So spin-orbit interaction, roughly, it goes in the order of roughly 1 MeV to, let's say, 50 MeV, milli-electron volt. And you see this electron-electron interaction, the right-hand side, or electron-ion interaction, which is mostly coulombic in nature, that has a larger value. And you have this spin-spin interaction, which is your exchange interaction. We call it this exchange interaction, which you have this DM interaction, Julius-Camoria interaction, which is the asymmetric exchange interaction, because like Heisenberg's interaction. So this is an asymmetric interaction, unlike your Heisenberg's interaction. And you have this in a solid, you have a crystal field, you have electron-ionic interaction, you have kinetic interaction, because electrons are moving, they have certain kinetic energy. So there are a bunch of interactions present in your solid, and the ranges of their energy goes like this. So what I want to mention is that in conventional materials, if you consider that what I told you, the atomic spin-orbit interaction varies at Z to the power 4, you will find in conventional materials, the low Z materials, the spin-orbit interaction is not a very high value. It is bounded by roughly, you say the upper bound can be about 50 milli-electron volts. So what it is the effects, the spin orbit coupling, how does it help? So this is a textbook information, because there are many students who will get benefited from it. So you know that there is something called time reversal symmetry. When t goes to minus t, the spin out goes to down spin. And you know the time reversal symmetry, it respects, it preserves the Kramer's theorem or the Kramer's degeneracy. That means if there is the time reversal symmetry is maintained, you will get the expression like this: ek of k is the wave vector equal to e minus k down. This is what happens if you have a time reversal symmetry. Similarly, if you have an inversion symmetry, so then the ek up will go to minus ek down, and ek down will go to minus e of minus k down. Now what will happen if you consider both the equations above, considering both in a system, both time reversal symmetry is there and inversion symmetry is there. I know I assume that you understand what is inversion symmetry. That is the material that is the inversion symmetry. So then what we'll find, the ek up equal to ek down. That means you will not be able to distinguish. So you will have spin degeneracy into the picture, because the energy is the same, whether it is ek up or ek down, their energy is the same. It does not distinguish. So now what we'll have, this is an example I have given. Suppose you are considering as a material which has inversion symmetry, like FCC or HCP hexagonal structure, then what is happening if you consider a p orbital? So you know p orbital, so you will have these three bands here, px, py, pz, and at the gamma point, at the high symmetry point, what you find that, as I mentioned, each band is spin degenerate. That means there can be two states here, ek up, ek down. They're spin degenerate. So at the gamma point, you have a 6-fold degeneracy, because each band has spin degeneracy. So you will have at the gamma point 6-fold spin degeneracy. Now what you consider, you switch on the spin orbit interaction, but assume that your material is still preserves the inversion symmetry. So if you do that, what you find, there is a splitting of the bands. You can see that the splitting of the bands, but still the spin degeneracy is maintained because I told you each band will have off spin and down spin. The spin degeneracy is still maintained. But if you want to consider a material where the inversion symmetry is broken, like a material where the ferroelectricity comes because of the inversion symmetry is broken. So in those kind of system, crystal system where inversion symmetry is broken, you can see here when you switch on the spinner with interaction, each band which I was talking about, P band, where you had both upspin and downspin, they were doubly degenerate. Now what is, you can see each band is a spin split. So by this way, you can remove by switching on the spinner with coupling and considering a lattice or crystal system which breaks the inversion symmetry, you can remove the spin degeneracy. But again, you can see at the gamma point, which is the most symmetry point, we have still spin degeneracy there because they can map into each other. So that is what the spin orbit coupling does. Spin orbit coupling splits the bands and it removes the spin degeneracy. So now, as I mentioned, the spin orbit interaction energy strength is very small. So let us have a comparison. How does the spin orbit interaction strength evolves when we go from 3D transition metal like iron, cobalt, nickel, copper to 5D transition metals like iridium, osmium, platinum. And we know that as you go from 3D transition metals, from 3D transition metal elements to 5D transition metal elements, the atomic number increases. So, and in the left-hand side, I have shown you a figure. And here you can see I have plotted the radial distribution function of 3D, 4D, and 5D transition metal systems. Let's say 3D you consider iron, 4D you consider ruthenium, 5D you consider iridium. What you see here, this is the radial distribution function as a function of distance, some normalized distance that is plotted in the x-axis. But the message is the following. You can see the orbital, the radial distribution function, you can see the probability of finding electrons for 3D is very close. And here what is happened, because there is a narrow small region where the probability of finding electrons in 3D system is more. But here what you find in a case of 5D, the orbital is mostly extended. Here as if the orbital is narrowed down. And when the orbital is narrowed down, when you put 2 electrons in one orbital, you will have a large Coulomb energy. Because we know as you bring 2 electrons close together, you will have a large Coulomb energy. So that is why the 3D transition metal based systems, they show large electronic correlation. That means the Coulomb U is very high for the 3D transition metal elements. But as you go from 3D to 5D, as I mentioned, for 5D, the orbital is more extended. You can see the orbital is more extended. You can see that the probability of finding the electron even far away from the nucleus. So the orbital is more extended. When the orbital is more extended, if you put 2 electrons in an orbital, they are not very close together to each other, you will not find that much Coulomb energy. So what the conclusion we want to draw from this picture is that for a 3D transition metal, the electron correlation or Coulomb U is very large, and for 5D transition metals, the Coulomb U is small. But on the other hand, that is what I have marked here. You can see here, this is just slide image I have taken from Professor Takagi, Max Planck Stuttgart director. So now you can see Coulomb U decreases as you go from 3D to 5D, and the reason I mentioned because the orbitals are more extended in case of 5D as compared to 3D. But you could look at the spin-orbit coupling. As I mentioned, the spin-orbit coupling varies with z to the power 4. The more is the number, more is the atomic number, the more is the strength of spin-orbit coupling. And you can see as you are going from, I mentioned, the maximum you can go to 50 millielectron, 10 to 50 millielectron volt for 3D. You can see this is a mention of 10 millielectron volt. But when you go from 3D to 5D, you see the spin-orbit coupling increases even though it goes to 0.5 eV or 1 eV. So now you see for the 5D transition metal ions or the system that contains 5D transition metal ions, for example, iridium, because I'll be talking more about iridium, where the spin-orbit coupling is more and the Coulomb U decreases, So there, in this kind of systems, there is a subtle competition because the spinor with the coupling energy competes with the Coulomb energy because they are of same magnitude. But if you consider, so because of this, the competition between these two energy scales, this one is your Coulomb energy, another is spinor with coupling. So because of their subtle competition, I'll show you that they give rise to various, new physics and that arises emergent phenomena in this kind of iridium-based systems. But if you consider the 3D transition metal-based systems, there is no spinor coupling. You can consider it a perturbation, a small perturbation. You can trace it. It does not change the electronic structure or very much. If you do not consider in your Hamiltonian the spinor interaction for 3D transition metal-based systems, but for a 5D transition metal system, it has a bigger role. It has a bigger say. So the complete electronic structure changes because of the large value of spinor interaction in the iridium-based compounds. So another point before I go to the research materials. So what does this spinor, this relativistic effect? I told you this is a relativistic effect. And you know, I'm asking this question, those who want to study, the students, they should know, you know, the gold looks yellow. And but you know, the silver looks transparent. Why does it look like this? So the reason for this, or if you want to understand, you need to understand what the spinor bit interaction, this relativistic effect does to it. How does the relativistic effect affects the physics of a color between the gold and the silver? So I think the students will get it more clear. So what I want to tell that because of the relativistic effect, I told spinor with coupling the relativistic effect, but there is something called inert pair effect, or what I told you, why this gold looks yellow, but silver looks, there is no color for silver. So that comes from the inert pair effect, that the relativistic effect, I think you should look and you should understand what is. But the main idea of this is that there is an orbital contraction. Because of relativistic effect, there is an orbital contraction. So what you find that the let's say this conduction band, when there is an orbital contraction, the conduction band comes lower. So this is a, let's say, this is a normal insulator. We know this is a normal insulator. This is the valence band, and this is the conduction band, and there's a gap. And here what you see, the conduction band, as I mentioned, is coming down, and that is kind of overlapping with the valence band. So we call it, there is a band crossing. There is a band inversion is happening. So now the valence band is going to the EK space of the conduction band, and the conduction band, EK, part of the EK space is coming to the valence band. So we call it band inversion. And why does this happen? Again, the reason goes to the relativistic effect. And that is what the reason, if you understand why gold looks yellow and silver looks, then you will understand why the band, the conduction band comes down. So assuming this happens because of the relativistic effect, and they call it in some language, this is inert pair effect. So now this is the structure, and there is a band crossing here, there is a band inversion here. Now what you do, and I told you, if you are considering this high Z element, there is a strong spinor bit interaction. And now what you do, you switch on the spinor bit interaction. If you switch on the spinor bit interaction, the job of spinor bit interaction is that it mixes the states of various parities. That means if you switch on the spinor bit interaction, as I was mentioning, that it will open up a gap. So you see, in this case, down case, it's opening up a gap. And if it open up a gap without any states at the Fermi energy, we call it an insulator. We call it a band insulator. I'll come to what is meaning by band insulator. But sometimes what happens, because of the topological effect, even though you switch on the interaction, because of this inversion effect, so there will be some states connecting from here to here and from here to here, and we call it as a topological insulator. That means there are some states available in the bulk energy band gap of the material. So to get a topological insulator or to get an insulator, from a band inversion where the bands are overlapping. When you switch on the spin orbit interaction, either you can go to a topological insulator or a simple band insulator that we know, silicon. Silicon is a simple band insulator. So now, and sometimes what happens, if you look at this, if you switch on the spin orbit interaction at certain points in the Brillouin zone, at certain points in the K space, because of some crystalline symmetry, because of the symmetry of the crystal, underlying crystal, even though you switch on the spin orbit interaction, it's not able to open up a gap. That is what I have shown here. It is, even though you see at one side, at one K point, it has been able to open up a gap, but at another K point, you can see the right hand side, it is not able to open up a gap. And here, the two bands, they cross linearly within a small energy range, and this kind of material, we call it 3D Dirac semi-metal. So why do we call it 3D Dirac semi-metal? Because it has a linear dispersion, and all the dispersion along Kx, Ky, Kz, that disperses linearly. Unlike the case of graphene, unlike the case of topological insulator, where this dispersion is on the surface. So here, what happens in the bulk band, inside the material, the EK dispersion is linear along all Kx, Ky direction, and since it is linear, we call it 3D Dirac semi-metals. So this all arises, as I mentioned, because of two characteristics. One is the relativistic effect, why does the band will come down and why they will overlap. That is what band inversion, and that is one part of the story. And the other part of the story, when there is a band inversion, if you can switch on this spin orbit interaction, it will try to open up a gap, and depending upon the crystal structure, whether there will be some gap opening at every point, or you will have surface states, or you will have a 3D Dirac semi-metal. And this is what the similar picture is cartoon here. This is a paper in Nature Materials, latest paper, I think in 2021. Here you can see this is a band inversion is happening. There is a valence band, there is a conduction band. They are touching each other. And you see when you are introducing the spin orbit interaction, you can have a topological insulator where there will be some surface states in the gap here. It's not shown, but you will have some surface states. Or you can have a Dirac semi-metal or Weil semi-metal. I'll come to that, what is Dirac and Weil semi-metals from the point of view of what this material physics. So here you can have this Weil or Dirac semi-metal or topological insulators. So what I wanted to tell you is that in the underlying reason for this kind of things to happen is because of spin orbit interaction. So spin orbit interaction is very important, though we don't study much in the transition metal oxide, 3D transition metal oxides such as cuprates and manganites, but they have a prominent role when you go to high Z elements, and that completely changes the underlying electronic structure. You see, the bands are getting inverted, and you can have these topological effects like Dirac and Weil semi-metals, and this is what is this all arises because of spin orbit interaction. Now you see, as I mentioned, to see this one, this is the typical, and I've taken this one from this Chemical Reviews 2020. You see, we know this one. This is the semiconductor and insulator because there's a gap. And here you can see this is a metal because the conduction band and the valence band, they overlap each other at certain points in the K space. And I mentioned that this is a topological insulator. I told you how topological insulator is created. And because you can see here, there are some surface states here in the gap. And if you look at the resistivity, this is the semiconductor insulator resistivity goes like this. It diverges T equal to 0. And you know, for a metal, it is linear at high temperature. And you find it, there is it saturates at low temperature. And this low temperature saturation is because of your residual resistivity, because that arises from some impurities. There are some impurities in the material. So this is what is your resistivity for a metal. But if you look at the topological insulator, what I find is that I told you that you have some conducting states that's arising at the surface. And that is what, even though it is a topological insulator, you see, unlike a band insulator that we know, we are very familiar that the resistivity diverges at T equal to 0. But in a topological insulator, you see the resistivity does not diverge at T equal to 0, rather it saturates. And this saturation arises from the surface states that contributing to the conductivity. And as I mentioned here, because you see, I've written here semiconductor and insulator. Basically, I mean, there is not great difference. There is no physics point of view difference between a semiconductor and insulator, because here I have given a rough a calculation to convince you that suppose you have a semiconductor, you have a gap of 0.2 eV electron volt, and 0.2 5 electron volt is roughly around, so this is around 0.025 eV. And now you can calculate how many electrons are getting or charge carriers they are getting excited. Then we know you use the Boltzmann statistics, you will find this is roughly order of 10 to the power minus 2. That means if you do this one, I mean at room temperature, that is KT equal to 0.025 eV. If you are calculating, if you are considering a semiconductor which is a band gap of 0.25 eV, so this many number of charge carriers are excited into the conduction band. But similarly, if you consider let's say you are considering a semiconductor which has a band gap of 4 eV, then you know you are at room temperature, so room temperature energy is roughly this one, 0.025 eV. Then what you find is that the probability of the electrons getting excited to the conduction band is very, very small. You can ignore it, 10 to the power minus 35. Here it is 10 to the power minus 2. So this is the difference basically. There is no difference between a semiconductor and insulator. Here the probability of exciting the particles because of the small energy gap is more here. But here it is very small. You will not get any conduction because the band gap is too large. So now this is what about your topological, I mean this insulator. Similarly, as I mentioned in the last slide, you can have a Dirac and Weil semimetals. So what is the Dirac and Weil semimetals? So here what will happen, as I told you, you will have the linear crossing of bands. But as I mentioned, in a Dirac case, you will have this degeneracy, because according to Kramer's, I have told you that you will have this up spin and down spin. But here what will happen, you will have a poor pole degeneracy in case of a Dirac. But what will happen in a Weil, you have similar kind of linear crossing of bands, but here the degeneracy has been removed because you are putting something like, because you can only transform a Dirac material to a Weil semi-metal. So by, as I mentioned in the second slide, you need to break the inversion symmetry, or you need to break the time reversal symmetry. So this is like, I mean, so that is what they call it. The Weil semi-metal is a chiral in nature, because the chirality is coming into picture here. But in case of Dirac, because you are basically, as if you have two Weil nodes you are putting together, so the chirality goes away. So you call it as an achiral material, and this is a chiral material. So you can probe all the things, whether it is a Weil semi-metal, whether it is a Dirac semi-metal, whether it is a topological insulator. You can probe all the things by doing photoelectron spectroscopy, angle result photoelectron spectroscopy, because that will measure the states where it is where it exists, and it will show the nature of the dispersion, because for angle result photoelectron spectroscopy can measure this EK dispersion. But because we know that it is not always accessible, and there are difficulties in measuring those. So what I'll show you, is there any transport signature? Like I showed you here, for an insulator, the resistance versus temperature should be like this. For a topological insulator, the resistance versus temperature should be like this. And what should be the typical signature from transport? We call it Dirac or Weil semi-metal. So can we justify it from transport studies? So here, so as I mentioned, this all arises because of the strong spin-orbit interaction, and that is relativistic effect. And anyways, spin-orbit interaction is a byproduct of, I will tell, the relativistic effect. And what you find that if you can do this quantum interference, that means there is something called a quantum transport, interference transport. That means if you have a material and there are some very minimal disorder in your material, and there is something called weak anti-localization and weak localization, that effect arises because of interference. So that means one electron wave is coming this way and another is going like this way, and they need to interfere where they started. So between these two electron waves, if they are traveling and they are time reversed paths and they're traveling, they can interfere with each other. And how do they interfere? They can interfere either constructively or they can interfere destructively. So when there is an interfere constructively, so there is a probability of finding more electrons there. So we call it localization. So that means the resistance will increase. So that is what resistance will increase in weak localization effect. In other way, if you want to measure the magnetoconductance as a function of a magnetic field for a weak localization effect, both effects are quantum interference is the interference effect. In one case, you will get positive magnetoconductance. That means as you are applying magnetic field, your conductance is increasing as compared to zero field. But if you want to, if there is a strong spin-orbit interaction in your material, spin-orbit interaction introduces an extra phase that comes due to the Bell curvature. So generally it introduces a pi phase because of the extra phase that is added. So it can give rise to a destructive interference in a material where that is strong spin-orbit interaction. And because of that pi, two electron waves which are traversing in time reversed paths, they can interfere destructively. And in that case, what you will find that your magnetoconductance as a function, your conductance as a function of magnetic field that decreases, that means you get negative magnetoconductance. So this is one of the technique people follow to really know so whether there is a strong spin-orbit interaction is there or not. And there are, I'll show you, there are some formulas, there are some theories, there are some formalism. You can really feed your data and you can calculate what are the various characteristic magnetic fields starting from spin-orbit characteristic field. So the main message of this one is you can do this interference transport studies, and you can tell whether there is a weak localization or whether weak anti-localization. And weak anti-localization is a signature. It is one of the signatures. There are many regions where weak anti-localization can arise, but in mostly strongly spin-orbit coupled systems, you will have this weak anti-localization effect. So this is just to make you, to show you one of our data. So this is a, you see, this is a platinum thin film, and we have measured its resistivity. In other way, we have calculated its conductance. And you see, this is your delta sigma. Y-axis is the delta sigma, and this is the magnetic field we have applied. You can see this is negative, and for the convenience of understanding, we have shifted the graphs vertically. But you can see as we are applying the magnetic field, the conductance is decreasing, and that is negative magnetoconductance, which is the signature of this weak anti-localization effect in the context of this quantum interference physics. And there are other formalism for that, how to extract various parameters from this data. And this is one formalism. This goes in the name of Hikami-Larkin-Nagoka equation. What you can do, you can feed your data using some characteristic magnetic fields, and you can actually find out what are the characteristic magnetic field like BSO and other things. So this is, you can see by doing this, we can tell whether how strong is your spin-orbit coupling in this material, but just an indicator, this it should show if there is a strong spin-orbit coupling, it should ideally show there's the weak anti-localization effect, that is the conductivity decreases as you apply the magnetic field. And not necessarily that when you get negative magnetoconductance, always it is weak anti-localization, or always it arises from interference effect. There could be other reasons, but the data has to be featured with this formalism, and if it fits well with the formalism, it indicates, validates that you have weak anti-localization effect. So now, having understood this one, what is spin-orbit interaction? How does it help in inverting band? Then, or at least relativistic effect, how does it help in inverting the band? When there is a band inversion has happened, when you switch on the spin-orbit interaction, how it opens up a gap. And in certain cases, it cannot open up a gap because of the crystalline symmetry, underlying crystalline symmetry. And you can have, depending upon, you can have a Dirac semi-metal or topological insulator or a band insulator. And this is one of the work we have been doing when I was in Max Planck. So this was SR3 PBO, like I showed you for platinum, PB also is a high Z element, and it shows strong spin-orbit coupling. And you see, this is the cartoon picture of the band diagram. You oxygen 2p band, PB 6p band, and SR 4d band. As I mentioned, there is the overlapping of bands here. And ideally, if there is overlapping of band to some extent, to a narrower extent, you should get a semi-metal. And if you now what you do, you forget about this B, you come to the C. Now there is a overlapping of bands when you switch on the spin-orbit interaction. As I mentioned, at certain points it open up a gap, but at certain point in the brilliant zone, because of the high symmetry, because of the underlying crystalline symmetry, so there are various symmetry associated, mirror symmetry, rotational symmetry. So this is a involved thing, which symmetry will not allow the opening of gap. But I'm showing you in general that because of the underlying crystal symmetry of this material, you cannot open up a gap at certain point in the brilliant zone. At that point is linear, that shows the linear dispersion close to the Fermi energy, and this was predicted to be a this SR3 PBO or SR3 SNO. The crystal structure is like this. So SR is, you can see here, the whitish one, the silvery color one, and the strontium. Oxygen is sitting here at the middle of the cube, and PB is, the PB is at the corner. So this material is supposed to be based on the idea that I told you, that it can show Dirac-like physics, 3D Dirac physics. I'm not talking about the surface state topological insulator. I'm not talking about graphene. That also shows Dirac states. I mean, this is two-dimensional. So now what you find here, there is a three-dimensional Dirac cone coming into picture. I'll not get into the details, but as I mentioned you, I want to just connect our result. I told you, if there is a strong spin-orbit coupling, we did the similar compound, sister compound SR3 SNO, and you see this is your y-axis is the conductivity and x-axis is the magnetic field. You see there is a strong negative magnetic conductance, and this negative magnetic conductance, this has been fitted with the formalism of weak antilocalization, and this clearly shows weak antilocalization effect, indicating that the strong spin-orbit entanglement in this Dirac materials. Now, so again I told you that I'm repeating the idea where spin-orbit interaction plays a bigger role. And I told you spin-orbit interaction is more when Z is more, or Z is high, because the atomic spin-orbit interaction goes at Z to the power 4. This is a famous phase diagram everybody shows when they talk about spin-orbit interaction in condensed matter systems. So here you can see the phase diagram. It has been scaled U by T versus lambda by 2. Let me try to explain you what is it. So U is your Coulomb energy, and T is your bandwidth, or T you can do as kinetic energy, hopping energy, because you know the hopping energy determines the bandwidth. The more is the hopping, the more is the bandwidth. That's what we know from simple tight binding model. So now you see your x-axis is lambda by T, and lambda is spin-orbit interaction, and T is your hopping energy or the bandwidth. So you see, when U by T is small, that means U is very small. The correlation is very small. The Coulomb U is very small, or people call it Hubbard U. That means on-site Coulomb energy. So you see, these are kind of the simple metals or band insulators. So in a simpler way, I have put it here. You can see silicon, aluminum, sodium. Here, the U is very small. Lambda is also very small because they are not high Z elements. So you see, for this kind of material, silicon, aluminum, sodium, which are simple metals or band insulators, they have been studied very well. Now you come to the extreme U, where the Coulomb U is very large. So that is, and lambda is very small. What are the candidate materials? As I mentioned, Coulomb U is very large in 3D transition metal-based systems. Because the orbital is very constrained, the orbital is narrowed. So when put two electrons, there is a strong chance of getting highly repulsive. They are highly repulsive. The Coulomb is very large. So those kind of systems are cuprates and manganites. So, and they are called so-called Mott insulators, if you see the left-hand side. So these are also kind of extensively studied because of the alluring properties of cuprates, so-called the high TC superconductivity. They are extensively studied. Still, there are some open problems. We have not understood the cuprates, but they have been extensively studied. They are now also extensively studied. So this is about the large U and small lambda, because I told you small lambda for cuprates and manganites. Why? Because their atomic number is not that large, so the spin-orbit interaction is very small. Now you come to topological insulator or semi-metal, which has been studied, let's say, last 15 years. And now, what is this topological insulator? These are the compounds where initially studied, let's say, Bi to Ac through bismuth-based compound, because bismuth has large spin-orbit coupling, or you can consider the semi-metal like bismuth. So here the lambda is very large, because spin-orbit coupling is very large, because they are high Z elements. But the correlation is very small because they are not 3D. So this kind of material, it's studied for last 15 years, I would tell, extensively. And there is nothing much exciting now going on in this topological insulators. And now you go to the extreme level. Here I have shown you in this right-hand side figure, where U is very large and lambda is very large. Those are the systems which are known as heavy fermion systems or Kondo lattices. I don't know if the students can understand heavy fermion systems. Yeah, but again, it is a full research topic. What is heavy fermion and what is Kondo lattice? And they are the systems where U is very large and lambda is also very large. And you can see some of the compounds, like these are the compounds where you will get this large U and large lambda. And this kind of research is also extensively being studied over the years. Now I am asking the question that where do the iridates reach? Because I told you, if you go from copper, nickel, manganese to the 4D is ruthenium, and from ruthenium if you go to 5D, let's say iridium. So where does the iridium stands? So the iridium, as I mentioned, iridium shows a large spin-orbit coupling, but not that much electronic correlation, because if you remember my second slide or third slide, I showed you as you come from 3D to 5D, the Coulomb electronic correlation decreases. And there is a subtle competition because they compete each other. Their energy scales are equivalent. And because their energy scales are equivalent, what you see here is that this iridates, iridium-based compound or the oxide compound based on iridium, and they are the potential candidates because they are both the spin-orbit interaction and electron correlation. They compete with each other, and that gives rise to various new electronic phases. And this is the famous diagram by the, you can see here, this is the region of iridates where both lambda and U, they compete with each other. And you can see they give rise to various kind of new emergent electronic phases. I told you they give rise to wild semi-metal. I'll tell you now what is spin-orbit coupled Mott insulator. They give rise to topological Mott insulator. Sometimes they give spin liquid, this quadrupolar higher order magnetic ordering. And there is something called axial insulator. It is very similar to topological, one class of topological insulator, but there is a gap, and they show some nice magnetoelectric effects. So the main idea is what I want to tell. These are very new terms, but these are very exciting terms, and the research is going on this field now very much. So they give rise to various emergent electronic phenomena, and that comes because of the subtle interplay between this spin-orbit interaction and electron correlation of the Coulomb. So now let me tell you, give you one thing. I have told you how spin-orbit interaction changes the band structure. Let me tell you something about how spin-orbit coupling also in iridates. Because I told you iridate is the prominent candidate because it has strong spin-orbit coupling. And it is not a poisonous material, so people are like other 5D transition metal, osmium and other things, they are kind of a little bit poisonous. It's very difficult to work with them. but iridium does not have such problem because people work easily with iridium oxides. So let me try to motivate you here by giving an example, which is a fascinating example. Way back, this work was published in PR in 2008, and that is one kind of very important work in the spin orbit physics. So you see, if you look at this series of compound, we call it the sister compounds, Sr2COO4, Sr2RHO4, Sr2IRO4. What we are changing? We are just changing cobalt to rhodium to iridium. And cobalt is 3D transition metal, rhodium is 4D transition metal, and iridium is 5D transition metal. And I told you, if this compound is a metal, strontium cobalt O4, Sr2 cobalt O4 is a metal. When you go to rhodium, what I told you, as you go from 3D to 4D, the orbital gets extended. That means the electron have more, they can hop easily. So naturally, naively, somebody would think if Sr2CO4 is a metal, Sr2RHO4 will be also a metal with higher metallicity. And when I go to Sr2IRO4, in iridium, again the orbital is extended over more space. So then somebody should naively think that if Sr2RHO4 is a metal, from band structure point of view, it should be also a metal. But what we find surprisingly, that it is an insulator. So why it is insulator? Because from simple band structure point of view, it should be a metal. So here, to understand this, why it is an insulator, becomes the need for the spin orbit physics. So this is what I'm trying to explain you. Let me keep a track of time. So yeah, I have some time. So here what we do, you see iridium has a IR4, there are the 5D electrons. So you see 2, 2, 4, there are the 5D electrons. And we know if there are the 5D electrons, from simple band structure point of view, we know, and when iridium is put into the lattice, so there is a crystal field splitting. One is T to the level, another is EG level. And this T to the level can accommodate 6 electrons, but iridium 4 plus has 5 electrons. So that means T to the level is not full. This is what I'm showing here. If T to the level 1 band is not completely full, then we know from our simple band structure, from the definition that we read in Kittel, Ascot, Marmin, it should be a metal. Band structure point of view, simple band structure point of view. But it is not the case. Now what we do in the B picture, let us do not simple band structure, let us put some correlation. So you put some correlation that how are you, that is the on-site Coulomb energy. You know, even if you put in correlated systems, you put this on-site Coulomb energy, the bands get splitted. We call it lower Hubbard band and upper Hubbard band. So similarly, if you put the electron correlation into picture, there is a chance that this band, which was not filled completely, this can go like one band, and there is another band. This is one of lower Hubbard band and upper Hubbard band. And lower Hubbard band can take 5 electrons. So if this is the case, then this is the insulator. Then what we are experimentally observing, it might be true. But there is a caution here. When you put the Hubbard U or this U parameter, as I mentioned, for SR2IRO4, the Hubbard U or the Coulomb, the U term is not that high. Because I told you SR2IR4, the orbitals are very much extended. So the Coulomb U is very small. If that is the case, you will not be able to open up a gap by putting such a large U, which is not expected for iridates, because you will not get the large U. So putting an unimaginable large U to make it an insulator is not the right criteria. So then this picture goes wrong and this picture goes wrong. Now what you do, now you have splitted your bands, T2G bands and EG bands, because now you cannot ignore, I told you, spin orbit interaction in iridates, because they compete, their strength is high, they are order of 0.5 EV. So now what they do, the T2G level, they split it. They split, because you know spin orbit coupling splits the bands. I was showing you that you will get P bands, will get P3 by 2 and P half. Similarly, what you find here, the J bands, the T2G bands that get splitted to J 3 by 2 and J half here. And this is what when there is a splitting. Now this is what is the J effective 3 by 2 and J effective half band, this gets splitted. But if that is the case, you see still there is a overlapping. So it could be a metal. Only J effective, only if you consider spinor decoupling, this is a metal, which is not the case what we see in experimentally. Now what you do, because I told you in SR2IRO4 or iridium-based systems, there is a subtle competition between spin-orbit interaction and electronic correlation. Now what you do, you switch on the U here. A little U you switch on. When you switch on little U here, what happens? This band, this is a narrow band, and this band now gets splitted. That is why what you get here is that this is band is filled completely J effective band, half band, and this band is empty, and this all arising because of, and here somebody may ask, why could not you open up a gap here by putting a U? Because here you require a large U. Here you can open up a gap by putting a small U because the band, J effective band is very narrow. So that is the reason why, and this was reported in 2008, very important paper. People tried to understand why it is the SR2IRO4 is an insulator. Because theoretically from our textbook knowledge, it should be a metal. So that is why the spin orbit comes into picture, and that gives rise to how the completely electronic states completely changes because of the underlying spin orbit structure. And now we added, I had told you what is band insulator. So this is what is known as spin orbit Mott insulator. So SR2IRO4 is a spin orbit Mott insulator. This is a new terminology coming because until 2008, there was no term something like spin orbit Mott insulator. People know what is a Mott insulator because they know if there is one electron per site, this is your Mott insulator. If there is one electron per site, we know then this electron can hop to this site. Until this site is not filled, we know each site can take 2 electrons because a band can take 2 n electrons. So now the electron, it theoretically, ideally, according to band structure, if there is 1 electron per site, this electron can be able to hop to the next site, and this should be a metal. But we know Mott insulator is a special case which arises because of strong electronic correlation. Though this electron tries to hop here, but it will experience a large Coulomb energy which is not energetically favorable. That is why the electron will not hop, so we get in an insulating state. That is what Mott insulator. But band insulator we know, and this is typically the Mott insulator I'm talking about. When U equal to 0, typically you should get a metal because there is 1 electron per site. But you see, when they are introducing a large U by W equal to 2, W is your hopping term or bandwidth. You see, when U by 2, there is this band separates, like I told you, you will have a lower Hubbard band, you will have an upper Hubbard band. This lower Hubbard band is completely filled because each side has 1 electron. So there can be, this band is completely filled. Like I told you, there are 5 electrons. So the D band can take 10 electrons. So this band is completely filled and this band is empty. This gives rise to insulating character. And this is the underlying theme, is people understand it very well. Mott insulator, the underlying theme is the electronic correlation. Similarly, band insulator, we know from our standard textbooks, I told you, silicon, let's say. So here the band, the insulating state is characterized by counting the electrons. If each site has even number of electrons, then what you find, the band is completely filled, then we call it as a band insulator. Now, what we have studied in our textbooks, band insulator, then we have studied in our Mott insulator, then something came up in the backside. If I go, so something came up, there is something called spin orbit Mott insulator, because both physics is taking place here. You require spin orbit coupling, you require Mott physics, both physics you require to understand why SR2IRO4 is insulator. So this is one of the, now you knew some new insulator, like you know topological insulator, you know band insulator, you know Mott insulator, you know spin orbit Mott insulator. And when I was talking about this weak localization, weak anti-localization effect, there something comes. I did not talk to you about this Anderson insulator. So there are various kind of insulator, and all this happens because of the reorganization of electrons or the competition between various energy scales. Another compound now I want to, madam, how much time I have?
Sir, you can continue.
Okay, very good. So another compound we have is SRIRO3, which is the sister compound, like what I told you, SR2IRO4. You see, the SRIRO3 is more three-dimensional compound compared to SR2IRO4. So this is what I told you, SR2IRO4 is an insulator. This is a spin orbit Mott insulator. And I told you that this lower Hubbard band is filled, upper Hubbard band is empty. That is why it is given as to spin orbit Mott insulator. But when you go to SRIRO3,
Sorry, sir, we cannot hear your voice. There is some network issue, maybe. We can see the slides, but voice is not audible.
Devakan sir. Devakan sir, can you hear me? I think some network issue is there.
Yes, madam. Devakan sir is there.
So some network issue is there. So sir will join again. Okay, connected.
Hello, sir.
Sir, your voice is not coming. Screen is visible. Sir, unmute, please.
Yeah. Now can you hear me?
Yes.
Okay.
Yes.
Okay. So we are in this slide. I'm sorry for this little bit technical glitches. Okay.
So kindly do it in the full
So
screen
this is
mode.
what I'm talking about. SRIRO3. It is already full screen.
Okay.
So SRIRO3 it should be a metal because as I mentioned, as you increase the dimensionality, the bandwidth increases. This is a very important thing. As you increase the dimensionality, the bandwidth increases. So now if the bandwidth increases, then this upper Hubbard band, lower Hubbard band bandwidth will increase and they will merge with each other. So that is why you should get a metal. But in real life, what we see, SRIRO3 is just semi-metal. So this is some theoretical band structure calculation. You see alpha equal to 0, that means no spin-orbit coupling. They see it is a metal because this is your Fermi energy. There are bunch of states close to the Fermi energy. But when you put the spin-orbit interaction alpha equal to 1.5, you see there are very less number of states at the Fermi energy that is indicating it is a semi-metallic state. And more importantly, what you see, there is a crossing of bands in this point at U point. There is a crossing of bands, and it gives rise the signature of a Dirac electron structure. And this is the typical semi-metallic state because for a semi-metal, the resistivity does not sensitively depends upon the temperature. So what we do want to do, so this was kind of the theoretical prediction. And there have been some RPS study, angle digital photoelectron spectroscopy study to understand the Dirac nature of the SRIRO3, but there has not been any transport studies where we can validate that yes, this SRIRO3 is a spin-orbit coupled material or Dirac semi-metal. So to do that, we have done something, but I'm not getting into the details. We have grown SRIRO3 thin films on an antiferromagnet 16 nanometer. This is SRCO2, which is an antiferromagnet. We have grown SRIRO3 and we have studied. This is, I told you, this is kind of the weak localization effect that comes from the spin-orbit coupling. You see the resistance is increasing. And we see for SRIRO3, there is a negative magnetoconductance, and we fitted with this equation that tells that there is strong spin-orbit coupling. But nothing gives a concrete evidence that, okay, SRIRO3 is a Dirac semi-metal. So here there is something called chiral anomaly induced negative magnetoresistance. This is a concept people use to ensure, to confirm whether a material is Dirac semi-metal, wild semi-metal or not. So what is it about? We know for doing all the magnetoconductance measurement, magnetotransport measurement, we are applying the magnetic field perpendicular to the sample plane or perpendicular to the current direction here, particularly. Here, what we are doing here, we are measuring the magnetoconductance by applying magnetic field and electric field same in the same direction. And I told you that I apply magnetic field because I told you Dirac is a four-fold degeneracy and it gets separated into two nodes, either like wild nodes. When you break the time reversal symmetry, that is what when you apply magnetic field, the Dirac node can get split into two nodes, like two wild nodes. This is one and this is one. And now when we apply electric field, one node will be more populated. You see there are more number of particle charge carriers correspond to the red one here. So when we apply electric field, the electrons will flow in one direction and there will be more populated. One node will be more populated, another will be less populated. And these two nodes, as I mentioned, are chiral. You can see they have some handedness. You can see the momentum direction is this one, spin direction is this one. This is having one chirality, one handedness. And if you go to the left one, the blue one, this is having opposite chirality, opposite handedness. And that is what the spin direction is this one, momentum direction is this one. This is one of the characteristic of wild nodes. They have different chiral nature. That is what I was mentioning you, how the Dirac node is different than the one is chiral, another is achiral. So here you have two chiral nodes, wild nodes. When you apply magnetic field, the Dirac node split. And now what will happen when you're applying electric field? So one node will be populated with more charge carriers. So that is why in this particular geometry, because ideally, classically, when we apply magnetic field and electric field in the same direction, you should not get any a change in the resistance. Because we know the Lorentz force works Q V cross B. And here it does not work because B is in the same direction, magnetic field in the same direction. But because of this chiral anomaly, it's basically a high energy concept, but people are using it to understand the kind of topological material. So this is what, because of the population difference between this chiral nodes, so the electron will flow from, the current will flow from one direction to another. This is, we call it an axial current. So that is what we call it here, because we got negative resistance. When you apply magnetic field, you got negative magnetic resistance, sorry. You get negative magnetic resistance. You see E is parallel to V, and this is, people are using it to probe various wild semi-metals. One of them is tantalum arsenide. This is the established wild semi-metal, and this is the typical thing you should expect if it is a wild semi-metal. Now let us come to our SRIRO3. I told you SRIRO3, ideally from naively band structure point of view, if you consider spin orbit and electron correlation, it should be a metal because of its dimensionality. But when you put spin orbit interaction, the band structure completely changes. It shows a direct structure in the electron spectra. So now, but there has not been any experimental evidence. And this is the test. If you can see the chiral anomaly induced negative magnetic resistance, and I'm not getting how we prepare the sample, what is the antiferromagnet is doing there, but now you see here, that means if you get negative magnetic resistance, in other way, you should get positive magnetic conductance. So now you see, we did the experiment, longitudinal magnetic conductance, that means B parallel to E. You see here, we are seeing positive magnetic conductance, and positive magnetic conductance in this particular geometry indicates there is a axial current which is arising because of this chiral anomaly. This is what we mean by the chiral anomaly. So details, you can look at it. So this confirms, and this chiral anomaly current is expressed like this, and this confirms, and we have seen how the C double changes. And main thing is, besides going into details, what I'm telling is, in the geometry B parallel to E, you should not expect any change in resistance because of magnetic field, because there is no Lorentz force classically. But here, because of this chiral anomaly, as I mentioned, you can have the current, you can have this positive magnetic conductance when applying magnetic field, and that is the reason, and this confirms that SRIRO3 is a Dirac semi-metal. And this is the research work I'll be finishing within a couple of minutes. And there are, this is the material cis family R2IR207. They call it pyrochlore. How does the pyrochlore structure looks like? This looks like this. That means the tetrahedra are corner shared. Each tetrahedra are corner shared. So iridium is there, and R2 can be neodymium, can be uridium, can be prosidium, can be, these are rare earth. And this spin structure of iridium in this structure shows a very, they call it all in all out. That means in each tetrahedra, this is a tetrahedra, each tetrahedra are connected, corners are connected, and each tetrahedra, the spin structure is like this. In each tetrahedra, either all spins are going out, in another tetrahedra, all spins are coming in. So you can have all in, all out, or all out spin structure. This is a very complex spin structure in this kind of iridates. And they are supposed to be semi-metal. You can see this EU2IR207, they are semi-metal. And it was predicted from this paper, it was a very important paper, it was predicted that this iridates can show this topological Dirac semi-metal. And how do you measure this one? And they told that this kind of materials within a relative value of the Coulomb EU, because I told you iridium is there, there's a strong spin-orbit interaction, and they can host this kind of Dirac and wild semi-metals. And there was a prediction that they should show anomalous Hall effect. If you see anomalous Hall effect, which arises because of the Berry curvature, because there is a strong, around the node, around the wild node, you will have this kind of a divergence of large, this Berry curvature. And because of that, it is related to this anomalous Hall effect. And in fact, the EU2IR207, particular this family compound EU2IR207, it was predicted that it will show this wild semi-metal phase. What is the check for that? Very simple check is, you should get anomalous Hall effect. And this is what the paper we recently published. This was done in collaboration with Professor P.S. Anil Kumar and his student at IISc. And this is published a couple of months back. And this is a magnetic wild semi-metal. As I mentioned, Dirac semi-metal, they preserve both time reversal symmetry and inversion symmetry. But if you want to go from Dirac to while, like what I told you, when you have a Dirac node, if you apply magnetic field, it will split into two while nodes. Similarly, to get this magnetic while semimetal or to while semimetal, you need to break either the time reversal symmetry or the inversion symmetry. And particularly this kind of material, EU2, IR27, and there have been many systems, there can be 4 or 5 systems where people have studied while semi-metallic phase in inversion symmetry broken systems. But there has not been many systems which are magnetically while semi-metal, where time reversal symmetry breaks. So here we have studied a system which we have claimed it that it is a magnetic while semi-metal. We have demonstrated it based on the theoretical prediction. As I mentioned, this is their spin structure. This is something extra diffraction, forget about all the things. As I mentioned, they show the semi-metallic behavior. There is a metal to semi-metal transition around 100K. This is resistivity versus temperature. And now what I mentioned, if they are, it is coming from the Berry curvature idea around the while node, and that it should show the anomalous Hall effect. Now we have measured the Hall effect. You see, this is rho xy versus, this is the Hall resistivity versus magnetic field. Now you see at a high field, it's linear, and high field it is linear, means that it's coming because of ordinary Hall effect. If you subtract the ordinary Hall effect from this data, you see you are getting a signature which is expected for this anomalous Hall effect, because it looks like a hysteresis. And this anomalous Hall effect that arises because of the while nodes present in EU2 IR207, and the while node arises because of the complex interaction between spin orbit scattering, underlying crystal structure, and the electronic correlation. Because that is what it was shown in this paper, that for a certain value of U in this pyrochlore family, you will explore this Dirac semi-metal or while semi-metal. And this is what we show here. This is one of the very interesting and exciting, because there has not been many systems where we can study the while metal semi-metallic phase in magnetic materials. And this is a magnetic materials because this is an antiferromagnet. Somebody may ask, you can have also anomalous Hall effect in ferromagnetic materials. Yes, we can have in ferromagnetic materials, but not in the antiferromagnetic materials. But the systems like this, where it is an antiferromagnet, but anomalous Hall effect arises because of these topological effects, because of the while nodes present in the EU2 IR207. So I will not get into this. So what I want to mention here, this is a very important paper where they are talking about you can have Dirac and while physics. There are various kind of things you can study because of the interplay between spin-orbit interaction and correlation. I told something about chiral anomaly, how chiral anomaly will give rise to a edge current, axial current, and that confirms the topological or the while nodes present in your system. I told you something about while semi-metals, and hello? Yeah, I'm finishing in a minute. So then there are some new topology may come up because of this while and this one, and there is something called axion insulators, which are very much like topological insulator, but there is a gap. And I told you they show exciting magnetoelectric effect. And there can be Foucault or driven states. So where you apply to this topological system, the while or this Dirac systems, you apply periodically perturbation, electromagnetic perturbation, and see, and this is a kind of one states. So I'm not much aware of these systems, but these are kind of various exciting physics you can do. And this is what if I want to do. So you see emergent phenomena from spin orbit coupling at surfaces interface. You can make thin films. You can get various kind of spin orbit coupling phenomena. Like I told you, Dirac and while, you can have Rasba effects because of spin orbit coupling. You can have a topological surface state. You have skyrmions because of spin orbit coupling. You can have spin charge conversion. You can have a tremendous amount of new physics that will arise because of spin orbit coupling in your material. So I'll not get into this. I think I have given you a very brief glimpse of what spin orbit interaction in a material. So thank you very much for your attention.
Thank you, Professor Saman. Starting from the breaking of spin degeneracy, we had a decent overview of importance of spin orbit coupling in high-jet elements and their effect on electronic structure. It was indeed a very good informative session about many fundamental concepts like Willy and Dirac physics, mode physics, chirality, and many more. So now we can take a couple of questions from the audience. The first question is, does the electron move inside the crystal at relativistic speed? How does the spin-orbit coupling come into picture?
Yeah, that's a very good question. So let me go there. So here, the electron does not move in this kind of system. So where is that one? Let me go there. Uh, uh, yeah, here the electrons don't move with the speed of whatever you are telling relativistic speed, but in this kind of materials, the mobility increases. So there is a high mobility in this kind of materials, but it never goes to the relativistic speed. We call it relativistic because of the linear dispersion.
Okay, sir. The next question is, how do the scattered electrons meet the coherence for interference?
Yeah, that's a good question. So here, everything we are talking about the coherence, because if it gets decoherence, we are talking about the interference between two coherent waves. That means the phase has already been retained. So that is what we are talking about, the coherent waves here. So even though they get scattered, but they retain their phase. So that is what we mean. If there is a magnet, that is what I have written here. Trajectory must be time reversal. Suppose you have a magnetic impurity. I'm talking about defects which are non-magnetic. If you have a magnetic impurity, there is a chance that it will not maintain that path. The phase breaking will happen. So that will give, we cannot study those kind of things based on this quantum interference effect. So what the electron wave we are talking about, the phase is maintained. So two coherent waves, they are interfering with each other.
Thank you, sir. Do we have any further questions? So if there are no more questions, then on behalf of Department of Physics, I would like to thank Professor Samal for such a wonderful presentation. Thank you, sir, for sharing your expertise with us. Thank you.
Sir, Devagan
Thank
sir.
you, madam.
Sir, I
Yeah.
have a few questions already. I have put in chat box. Prachi madam, I could not see probably. So about different type of insulators, you explain how we can classify based on spin orbit coupling.
So spin orbit coupling, as I mentioned, simple band structure point of view, we know what is band insulator, whether the band is completely filled based on electron counting or the band is not, band is partial filled. If band is completely filled, that is, we call it as a band insulator. But from spin orbit coupling, we are talking about only topological insulators. So the spin orbit coupling is giving rise to, even though the bulk is insulator, but it is giving rise to surface state. That is what we call it topological insulator. But other things what I told, those are not insulators, those are semi-metals. They are Dirac and Weil semi-metals. So there is no gap in the bulk band structure, bulk electronic spectra.
Yes, sir.
So based on this, we can only talk about spin orbit interaction given rise to topological insulator.
And sir, please explain that in IR system, the insulation behavior in IR system using
Okay,
that
insulating behavior. Okay, you are talking about SR2IR04?
Yes.
No, not insulator. Okay,
Yes, yes.
here what I am talking about, because this is an extended, I'm talking about for, so this is a sister compound of SR2CO4. So SR2CO4 is a metal. Then if you go from 3D to 4D, SR2RHO4 is also a metal.
Yes.
But when you go to SR2IRO4, naively, anybody will think it should be a metal because the iridium orbitals are extended here. The electrons can flow easily without any problem because there is not strong correlation. So naively, one should get it in a metal. One should think it is a metal. But in real life, when somebody measures it, it's an insulator. So how to understand this? Then this is what, when iridium is in a crystal, iridium is 4 plus in this system, and 4 plus means iridium, there are 5 electrons are there at each iridium site. So when there are 5 iridiums, you have T2G and EG level, that means T2G level has 5 electrons. So if T2G level is 5 electrons, we know that T2G level can take 6 electrons because there are 3 states. So it is not filled as you saw here in the A, then it should be a metal because the band is partial filled. But this is not the case. Now people thought maybe we'll switch on the large U. So this band will, the partial field band will now split into two bands. One is lower Hubbard band, one is upper Hubbard band. And lower Hubbard band will be filled because it requires 5 electrons. It will be completely filled, then it will be insulator. But this is not idealistic right, because in this particular SR2IR04, iridium does not have that much Coulomb U electronic coordination to open up a gap like this. So this idea also ruled out. Now what happened? You switch on this because we know that there is a spin orbit interaction in the iridium. So now you switch on the spin orbit interaction. So what will happen? Now T2J level will split into J effective states. One is J3 by 2, another is J half. And in J3 by 2, you have this one. What is this called? There will be 4 electrons. And in J half, there will be 1 electrons. So basically, you will have J half and J3 by 2. And they will be close together. And this is what we call it J effective band. But still, it does not talk about metal. It does not talk about insulator because they are close together. Now what happens if you introduce a small u? Because I told you, iridium, though they have small u, but there is a definite u for them. So now when you introduce u, your J effective half band, which was already half filled, now that will split into 2 bands. One is lower Hubbard band, another upper Hubbard band of J effective. So that is why now you see J effective band, lower Hubbard band is completely filled, but J effective upper Hubbard band is not filled. So this gives rise to an insulating character.
Yes, sir.
So that means there is a subtle competition between the spin orbit and the electronic polarization.
Thank
So
you.
as you asked me, I will tell you, I introduced 2 insulators. One is topological insulator, another is spin orbit mode insulator in my talk, which arises from underlying spin orbit interaction.
Yes, sir. Thank you for the nice explanation. And I want to invite you to talk to our students and to us through physical mode. It will be more interesting.
Okay, yeah, madam. Okay, madam.
Okay.
So that's all for the session of the day 2 of the EDV. We all will meet again as per the scheduled time, that is 9:30 a.m. tomorrow. Thank you.
Thank you.
Thank you, everyone.
Thank you, sir.
Thank you.